Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the depths of space and time, where stars are born in cosmic nurseries and our sun may once have had a twin. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need the moment of stillness too. And to those who've already joined along, thank you. In the vast darkness between stars, where space seems empty and silent, enormous clouds of gas and dust drift through the galaxy like cosmic fog. These molecular clouds, some spanning hundreds of light years, contain the raw materials for stellar birth. Each cloud holds enough matter to create thousands of stars, yet it drifts through space with the density of Earth's best laboratory vacuum. The contradiction settles into the mind with gentle irony. What appears empty actually teems with the building blocks of stellar creation. The clouds move through galactic space at speeds that would terrify terrestrial travelers, racing at tens of thousands of miles per hour around the galaxy's center. Yet from the perspective of cosmic time, they barely seem to move at all. A molecular cloud maintains its basic structure for millions of years, its vast bulk rotating slowly like a celestial carousel made of hydrogen and helium, sprinkled with heavier elements forged in the nuclear furnaces of long-dead stars. Within these stellar nurseries, temperatures hover just above absolute zero, creating conditions more frigid than any earthly winter. At negative 400 degrees Fahrenheit, matter exists in a state of patient waiting that spans geological ages. Water molecules freeze solid to dust grains, forming tiny crystals that drift like microscopic snowflakes through the interstellar medium. Carbon monoxide, ammonia, and dozens of other simple compounds coat these frozen particles, creating a vast library of chemistry suspended in the cosmic cold. The darkness between the dust grains stretches for distances that dwarf planetary scales. If a dust particle were enlarged to the size of a marble, its nearest neighbor would sit several miles away. This profound emptiness creates a silence more complete than any earthly quiet. No air to carry sound waves, no atmosphere to generate weather, just the gentle electromagnetic whispers of molecules absorbing and emitting radiation at radio wavelengths. Gravity works slowly but inevitably in these stellar nurseries, like a cosmic sculptor chiseling away at raw material with infinite patience. Tiny variations in density, perhaps triggered by the shockwave from a distant supernova or the gravitational influence of a passing star, create seeds of future stellar systems. These density fluctuations represent mere whispers of change, regions where the cloud contains perhaps one extra hydrogen molecule per cubic meter. Yet these microscopic variations will eventually determine where stars ignite and where empty space remains. The process unfolds with the geological patience that makes mountain formation seem hurried by comparison. Gas molecules drift together grain by grain, building mass so gradually that a human lifetime represents barely a whisper in the cloud's transformation. Generations of civilizations could rise and fall, while a single stellar nursery prepares for its moment of birth. The universe operates on timescales that render human urgency meaningless, transforming vast regions of space through processes so gradual they approach the meditative. Magnetic fields thread through these molecular clouds like invisible highways, guiding the motion of charged particles and creating structure within apparent chaos. These magnetic lines of force, thousands of times weaker than a refrigerator magnet yet spanning light years in extent, help determine how collapsing gas will fragment into individual stellar cores. The interplay between gravity, magnetism, and turbulence creates a delicate balance that has persisted unchanged since the galaxy's youth. Only after countless millennia does the accumulating matter reach the critical threshold where collapse becomes inevitable. The transition happens gradually, then suddenly, like a landslide that builds tension grain by grain until the entire mountainside surrenders to gravity. Dense cores within the cloud begin contracting faster than sound can travel through the rarefied gas, creating regions of increasingly concentrated matter that will eventually ignite nuclear fusion. When stellar birth finally begins, it rarely produces solitary stars like hermits in the cosmic wilderness. The collapsing cloud fragments into multiple dense cores, each destined to ignite its own nuclear furnace. Stellar twins and triplets emerge from the same gravitational womb, born within astronomical distances of each other but linked by invisible threads of mutual gravitational attraction. The universe seems to prefer stellar partnerships, cosmic companions locked in gravitational embrace for billions of years. Binary star systems dominate galactic stellar populations with quiet persistence. More than half of all stars exist in gravitational partnerships, their orbital dances spanning timescales that make geological epochs seem brief. Some stellar twins orbit each other in hours, their surfaces nearly touching as they whirl through space like cosmic figure skaters. Others maintain distances measured in light years, taking millions of years to complete a single orbital revolution around their common center of mass. The mathematics of stellar companionship creates endless variations on gravitational themes. Stars can orbit in perfect circles, long ellipses, or complex patterns that trace intricate geometric shapes across centuries. Mass ratios determine the choreography. Nearly equal stars dance as partners, while mismatched pairs create systems where massive primaries dominate tiny secondary companions. The universe has been experimenting with these gravitational arrangements for over 13 billion years. This preference for stellar twins presents a quiet mystery that hangs in the darkness like an unanswered question. If most stars form in pairs or groups, why does our sun drift through space alone? The statistical improbability settles into contemplation with gentle weight. Our solar system's solitary architecture may represent an exception rather than the rule. Perhaps our star once had a companion that vanished into the galactic night, leaving behind only subtle gravitational echoes in the arrangement of distant comets. The search for our sun's hypothetical twin has occupied astronomers for decades, though the evidence remains frustratingly elusive. Computer simulations of stellar formation suggest that single stars like our Sun should be uncommon. Yet here we orbit a solitary nuclear furnace that appears to have always travelled alone. The contradiction creates a cosmic puzzle that may never find complete resolution. The irony settles gently over this cosmic meditation like stellar dust accumulating over eons, in a universe where stellar loneliness appears unusual. Our Sun carries its family of planets through space as a singular entity. Only took 4.5 billion years to notice we might be different. The molecular clouds continue their patient work, birthing new stellar partnerships while our solitary star maintains its quiet journey through the galaxy's spiral arms, perhaps mourning a companion it never had, or perhaps celebrating an independence that allowed the delicate chemistry of life to flourish on a small blue world. In the deepest cold of interstellar space, where stellar nurseries drift between the galaxy's spiral arms, the raw materials for countless future suns continue their ancient wait. The process that created our Sun continues unchanged, patient and inevitable as cosmic time itself. 4.5 billion years ago, in a region of space that no longer exists in its original form. Our sun ignites its nuclear furnace for the first time. The moment arrives without ceremony or cosmic fanfare, simply the inevitable culmination of gravitational collapse that has been building for millions of years in the dense core of what will become our solar system. Temperatures reach 10 million degrees Celsius, hot enough to fuse hydrogen nuclei into helium and release the energy that will sustain life on distant worlds not yet formed. The young sun burns with unstable fury during its earliest years, fluctuating in brightness as it settles into the steady nuclear rhythm that will define the next 10 billion years. Solar flares erupt from its surface with violence that would sterilize any nearby planets, sending streams of charged particles racing outward at speeds approaching that of light. The stellar wind, a constant stream of plasma flowing from the sun's corona, blows with hurricane force, carrying away excess angular momentum and gradually slowing the star's rotation from hours to the month-long period it maintains today. Around this newborn star, a disk of leftover material spreads outward like cosmic pizza dough, containing all the raw ingredients for planetary formation. Dust grains no larger than smoke particles begin the patient work of accretion, sticking together through electrostatic forces and van der Waals attractions. These microscopic building blocks will eventually construct entire worlds, but their initial aggregation unfolds with geological slowness that makes continental drift seem hurried. The early solar system exists in a state of controlled chaos, with countless small bodies orbiting in roughly the same plane but following paths that frequently intersect. Collisions happen constantly as planetesimals. Rocky bodies ranging from pebbles to mountains smash together with energies that melt rock and vaporize ice. Most of these impacts result in mutual destruction, but occasionally two bodies stick together, growing incrementally larger through a process astronomers call accretion. Yet in this cosmic construction zone, our sun burns alone. No stellar companion shares the gravitational dance of planetary formation. No second star disrupts the delicate orbital mechanics that will eventually produce Earth's stable, nearly circular path around its primary. The absence creates a profound difference from most stellar systems, where binary companions create complex gravitational environments that can fling planets into eccentric orbits or eject them entirely from their parent systems. The solitary nature of our early solar system allows for architectural precision that would be impossible in a binary arrangement. The inner rocky planets form in orderly progression Mercury, Venus, Earth, and Mars, each occupying a stable orbital niche determined by temperature gradients and the availability of different materials. Further out, where water can remain frozen, the gas giants accumulate massive atmospheres by capturing hydrogen and helium directly from the solar nebula. This planetary construction project unfolds over tens of millions of years, with each world growing through countless individual collisions. The process resembles cosmic archaeology in reverse. Instead of uncovering layers of the past, gravity builds up layers of the future. Every meteorite that strikes a growing planet adds not just mass, but also the complex chemistry that will eventually enable geology, weather, and perhaps even life. The mystery of our sun's solitude deepens when viewed against the broader context of stellar formation. Computer models suggest that stars forming in isolation should be extremely rare. Yet our solar system shows no clear evidence of ever having possessed a binary companion. The chemical composition of our sun matches that of single stars, rather than systems that have experienced the complex gravitational interactions typical of binary evolution. Some astronomers propose that our sun formed in a dense stellar cluster, surrounded by hundreds or thousands of sibling stars born from the same molecular cloud. In such an environment, gravitational interactions could gradually strip away potential companions, leaving our Sun to drift into galactic isolation. The process would unfold over millions of years as the stellar cluster slowly dispersed, with individual stars following different orbital paths around the galaxy's center. The timing of our Sun's stellar ignition represents another quiet irony in cosmic history. Our star begins its nuclear burning at precisely the moment when the galaxy has achieved the right balance of heavy elements created by previous generations of stellar death to enable the formation of rocky planets. Too early and insufficient carbon, oxygen, and silicon would exist to build terrestrial worlds. Too late, and the galaxy's star formation rate would have declined too far to provide the stellar nursery environment necessary for planetary system architecture. During its first 100 million years, our young Sun gradually settles into the stable main sequence burning that characterizes middle-aged stars. The violent fluctuations of stellar youth give way to the steady nuclear fusion that will continue for another 5 billion years. Solar luminosity increases slowly but persistently, providing the gradually warming environment that will eventually drive the evolution of Earth's climate and the emergence of complex life. The early Sun's radiation pressure gradually clears away the remaining dust and gas from the inner solar system, like a cosmic wind sweeping clean the space between newly formed planets. This process, called photoevaporation, marks the end of rapid planetary growth and the beginning of the more stable gravitational environment that characterizes mature planetary systems. The leftover debris migrates outward or falls into the Sun, leaving behind the orbital architecture that remains essentially unchanged today. It only took a few 100 million years to create a perfectly balanced system. 8 major planets, dozens of moons, and countless smaller bodies arranged in gravitational harmony around a solitary star. The absence of a stellar companion allowed this delicate construction to proceed without the disruptive influences that characterize most binary systems, where gravitational chaos often prevents the formation of stable, habitable worlds. In the quiet aftermath of planetary formation, our Sun continues its solitary journey through the galaxy, carrying its family of worlds through the cosmic dark. The stellar nursery that gave it birth has long since dispersed, its constituent stars scattered across the galaxy's spiral arms. Our Sun drifts alone, neither seeking nor avoiding stellar companions, following an orbit around the galactic center that will take 200 million years to complete. Across the galaxy's spiral arms, in stellar neighborhoods both near and impossibly distant, binary star systems perform their ancient gravitational choreography with mathematical precision. More than half of all stars exist not as solitary entities like our Sun, but as gravitational partners locked in orbital dances that span timescales measured in cosmic epochs. These stellar twins, triplets, and complex multiple systems represent the galaxy's preferred arrangement, a cosmic social order where stars rarely travel alone through the interstellar dark. The nearest binary system to our solar system lies just over 4 light-years away, in the triple star arrangement known as Alpha Centauri. Here, 2 sun-like stars orbit each other every 80 years, while a third smaller companion, Proxima Centauri, follows a much wider orbit that takes hundreds of thousands of years to complete. The system serves as a reminder of how unusual our solitary Sun appears in the galactic context. Even our closest stellar neighbors exist in gravitational partnership, their combined light creating the single bright star visible to naked-eye observers on Earth. Binary stars form through the same processes that create single stars, but with subtle differences in initial conditions that lead to profoundly different outcomes. When a collapsing molecular cloud fragment contains enough angular momentum, it naturally splits into two or more cores rather than forming a single massive object. The physics resembles a figure skater spinning faster as she pulls in her arms. Except in reverse, the contracting gas cloud spreads its rotation across multiple centers of mass, creating the foundation for stellar partnerships that will persist for billions of years. The orbital mechanics of binary systems create an endless variety of gravitational arrangements, each following the same fundamental laws that govern planetary motion but scaled up to stellar masses and distances. Some binary stars orbit so closely that their outer atmospheres actually touch, creating contact binaries where stellar material flows between the two stars like a gravitational waterfall. These systems complete orbital periods in mere hours, whirling around each other with speeds that would tear apart any solid body through centrifugal force. At the other extreme, wide binary stars maintain separations measured in thousands of astronomical units, distances so vast that light takes hours to travel between the stellar companions. These widely separated pairs take millions of years to complete a single orbit, their gravitational connection so tenuous that passing stars or molecular clouds can sometimes disrupt their ancient partnership. The orbital periods stretch beyond the timescales of biological evolution, making each revolution a cosmic epoch in its own right. The gravitational dance between binary stars creates complex patterns of stellar motion that astronomers have studied for centuries. When two stars of similar mass orbit each other, they revolve around their common center of mass, a point called the barycenter that lies roughly midway between them. More massive stars dominate their smaller companions, creating systems where tiny red dwarfs orbit massive blue giants, like stellar moths circling cosmic flames. The mathematics of these orbital relationships follow the same principles that Johannes Kepler discovered for planetary motion, but applied to objects containing the mass of hundreds of thousands of Earths. The diversity of binary star arrangements extends far beyond simple pairs. Triple star systems often feature a close binary pair orbited by a more distant third star, creating gravitational hierarchies that remain stable for billions of years. Quadruple systems exist where two binary pairs orbit around their shared center of mass, forming gravitational structures of breathtaking complexity. Some star clusters contain dozens of stars bound together by mutual gravitational attraction, creating stellar cities where individual stars follow orbits as complex as the paths of comets in our solar system. The evolution of binary stars unfolds through processes unknown to solitary stars like our Sun. When one member of a binary pair exhausts its nuclear fuel and begins to expand into a red giant, it may transfer material to its companion through gravitational tides. This mass transfer can rejuvenate the receiving star, extending its main sequence lifetime far beyond what would be possible in isolation. The donor star, meanwhile, may shrink to become a white dwarf while its companion burns with renewed nuclear vigor fueled by stolen stellar material. Some binary systems create the most violent events in the observable universe. When a white dwarf star accretes enough material from a binary companion, it can trigger a thermonuclear explosion called a Type Ia supernova, an event so luminous that it outshines entire galaxies for months. These stellar explosions serve as standard candles for measuring cosmic distances, their consistent peak brightness allowing astronomers to map the universe's expansion across billions of light years. The irony settles gently into contemplation. Stellar companionship sometimes leads to mutual destruction on scales that dwarf terrestrial imagination. Binary star systems also create the most precise timekeepers in the universe. Pulsar binary systems, where a rapidly spinning neutron star orbits a stellar companion, maintain orbital periods stable to within nanoseconds over decades of observation. These cosmic chronometers tick with accuracy that exceeds the best atomic clocks. their gravitational waves carrying away orbital energy so slowly that the stars spiral inward at rates measurable only over centuries. The 1993 Nobel Prize in Physics honored the discovery of gravitational wave energy loss in binary pulsars, confirming Einstein's predictions about the fundamental structure of space-time. The search for planets around binary stars has revealed worlds existing in gravitational environments of stunning complexity. Some planets orbit just one member of a binary pair, experiencing the gravitational influence of two stars but receiving heat and light primarily from their primary parent. Other planets follow circumbinary orbits, revolving around both stars simultaneously like cosmic figure eights traced across the sky. These worlds experience double sunsets and gravitational tides that create climate patterns impossible in single-star systems. The habitability of planets in binary systems depends on delicate orbital mechanics that determine whether liquid water can exist on planetary surfaces. Close binary stars create regions where gravitational perturbations prevent stable planetary orbits, leaving gaps in the orbital architecture where no worlds can form. Widely separated binaries allow for Earth-like planets around individual stars, but subject them to long-term climate variations as the stellar companions follow their extended orbital dance. The temperature of such worlds fluctuates over timescales of thousands or millions of years, creating evolutionary pressures unknown on Earth. The statistical dominance of binary stars throughout the galaxy raises profound questions about the rarity of solitary systems like our own. If stellar companionship represents the cosmic norm, then the conditions that allowed Earth's stable climate and the emergence of complex life may be far more unusual than previously imagined. The delicate gravitational balance that maintains Earth's nearly circular orbit might be impossible in binary systems, where stellar companions create orbital perturbations that drive planets into eccentric paths unsuitable for biological evolution. Modern astronomical surveys continue to discover new types of binary systems, each adding complexity to our understanding of stellar partnerships. Eclipsing binaries, where the orbital plane aligns with Earth's line of sight, allow astronomers to measure stellar masses and radii with extraordinary precision. X-ray binaries, where matter from a normal star falls onto a neutron star or black hole companion, creates some of the brightest objects in the galaxy at high-energy wavelengths. Symbiotic stars feature white dwarfs accreting material from red giant companions, creating nova explosions that repeat over cycles of decades or centuries. The galaxy's preference for stellar partnerships extends to the smallest scales of stellar formation. Even brown dwarfs, failed stars too small to sustain nuclear fusion, often exist in binary arrangements. Their weak gravitational bonds creating systems where objects with the mass of large planets orbit each other like diminutive stellar twins. These brown dwarf binaries blur the distinction between planetary systems and stellar partnerships, occupying a transitional realm between worlds and stars. Only took 13 billion years of cosmic evolution to create this vast diversity of stellar relationships. Countless binary systems performing their gravitational ballets while our Sun drifts alone through the interstellar medium. The statistical weight of stellar companionship presses gently against the mystery of our solar system's isolation, creating a quiet tension between what appears normal in the galaxy and what we observe in our own cosmic neighborhood. Perhaps our Sun's solitude represents not a cosmic accident, but a necessary condition for the emergence of the stable, temperate worlds that harbor the chemistry of life. The binary stars continue their ancient dances, marking time in orbital periods that span from hours to millions of years, while our solitary sun maintains its steady journey through the galaxy's spiral arms, carrying its family of planets through the cosmic dark without stellar companionship or gravitational interference from neighbouring stars. In the 1980s, paleontologists noticed a disturbing pattern hidden within the fossil record of Earth's history. Mass extinctions, those catastrophic events that sweep away entire families of species, appear to occur with clockwork regularity every 26 million years. The statistical correlation was too precise to ignore, too consistent to attribute to random cosmic accidents. Something in the depths of space seemed to be triggering periodic waves of biological destruction with the reliability of a cosmic metronome, counting out Earth's geological epochs in units of extinction and recovery. The mystery deepened when scientists realized that these extinction events often coincided with evidence of increased comet impacts. Craters dating to periods of mass die-offs suggested that swarms of icy bodies had periodically rained down from the outer solar system, their impacts creating the environmental chaos necessary to disrupt global ecosystems. But what could cause such regular disturbances in the normally stable realm of comets that orbit far beyond Pluto's distant path? Astronomers proposed an elegant but unproven solution. Nemesis, a hypothetical stellar companion to our Sun, this dark star would follow an extremely elongated orbit, approaching the outer solar system every 26 million years before retreating into the interstellar darkness. During each close passage, Nemesis would gravitationally disturb the Oort Cloud, that spherical shell of trillions of comets that marks the edge of our Sun's gravitational domain, sending cascades of icy bodies tumbling inward toward the inner planets. The physics of such a system would create precisely the kind of periodic disturbance observed in Earth's extinction record. A stellar companion following a highly eccentric orbit would spend most of its time far from the Sun, invisible and harmless. But during perihelion, its closest approach, Nemesis would plough through the outer regions of the Oort Cloud like a gravitational bulldozer, scattering comets in all directions and increasing the probability of Earth impacts by orders of magnitude. For Nemesis to remain undetected despite decades of astronomical surveys, it would need to be remarkably dim, perhaps a red dwarf star burning with barely 1,000th the luminosity of our Sun, or even a brown dwarf that never achieved full stellar ignition. Such an object would radiate primarily in infrared wavelengths, making it nearly invisible to optical telescopes but detectable by sensitive heat-seeking instruments. The irony of this cosmic hide-and-seek game settles into contemplation. Our Sun's hypothetical twin might be the faintest, most elusive member of the stellar community. The orbital mechanics required for the Nemesis hypothesis present their own challenges to astronomical imagination. To produce 26 million-year periods, this stellar companion would need to orbit at distances of approximately 1 to 3 light-years from the Sun, roughly halfway to the nearest neighbouring stars. Such a vast elliptical orbit would be extraordinarily vulnerable to disruption by passing stars or giant molecular clouds, making long-term stability questionable over the billions of years required for multiple extinction cycles. Computer simulations of the proposed Nemesis orbit reveal additional complications that cast doubt on the hypothesis. A stellar companion following such an extreme elliptical path would likely have been stripped away by galactic tidal forces long ago, particularly during the Sun's youth, when it may have been part of a dense stellar cluster. The gravitational environment of the early galaxy would have been far more chaotic than today, with frequent close encounters between stars that could easily disrupt weakly bound binary systems. The search for Nemesis has engaged some of astronomy's most sophisticated instruments, from ground-based infrared surveys to space-based telescopes designed to catalogue every faint star in the Sun's neighbourhood. The Wide Field Infrared Survey Explorer, WISE, mapped the entire sky in infrared light, detecting objects as cool as room temperature out to distances of several light years. If Nemesis exists as a brown dwarf companion, WISE should have found it glowing dimly in the heat signature of its own gravitational compression. Yet despite these comprehensive searches, Nemesis remains stubbornly absent from astronomical catalogues. No dim red dwarf or brown dwarf has been discovered following an orbit consistent with the extinction periodicity. The failure to find direct evidence has gradually shifted scientific opinion away from the Nemesis hypothesis, though the underlying pattern of extinction periodicity continues to puzzle paleontologists and astronomers alike. Alternative explanations for the extinction cycle have emerged that do not require a stellar companion. The Sun's orbit around the galaxy carries our solar system through regions of varying stellar density and cosmic ray intensity. Passage through spiral arms or molecular clouds might trigger climate changes severe enough to cause mass extinctions. Though the timing of such galactic encounters does not align well with the observed 26 million year pattern, other astronomers propose that the extinction periodicity might be an artifact of incomplete fossil data rather than evidence for astronomical causes. The geological record becomes increasingly sparse and difficult to interpret as researchers examine older rock formations, potentially creating apparent patterns where none actually exist. Statistical analysis of extinction timing remains contentious, with different methods producing different results depending on which events are included and how ages are determined. The concept of Nemesis has also inspired broader searches for stellar companions that might not follow such extreme orbits. Wide binary systems, where stellar companions orbit at distances of thousands of astronomical units, represent a more plausible arrangement that could have persisted since the solar system's formation. Such companions would take hundreds of thousands of years to complete their orbits, creating gravitational influences too gradual to explain periodic extinctions, but potentially detectable through precise measurements of stellar positions. The mystery of Earth's extinction pattern reflects larger uncertainties about the frequency and causes of mass die-offs throughout geological history. Each extinction event results from complex interactions between astronomical, geological, and biological factors that make simple causal relationships difficult to establish. Asteroid impacts, volcanic eruptions, climate changes, and evolutionary pressures all contribute to the background rate of species turnover, creating a noisy signal from which periodic patterns may or may not emerge. Modern paleontology has identified at least 5 major extinction events in Earth's history, from the Ordovician die-off that eliminated marine life 400 million years ago to the Cretaceous impact that ended the age of dinosaurs. Each event left distinct signatures in rock formations and fossil assemblages, but their timing shows no clear astronomical correlation. The supposed 26 million year cycle may be a statistical coincidence rather than evidence for cosmic clockwork. The search for Nemesis represents astronomy's attempt to find simple, elegant explanations for complex biological phenomena. The idea of a dark stellar companion controlling Earth's evolutionary history appeals to the scientific preference for unified theories that connect disparate observations. Yet the universe often proves more complicated than our desire for mathematical beauty suggests, with multiple factors contributing to outcomes that resist reduction to single causes. Only took 30 years of searching to realize that our sun's hypothetical executioner might never have existed at all. The absence of evidence gradually becomes evidence of absence. Though the original mystery of extinction periodicity remains as puzzling as ever, perhaps Earth's biological history unfolds according to its own internal rhythms, rather than responding to the gravitational metronome of a stellar companion hidden in the cosmic dark. The nemesis hypothesis fades into the realm of fascinating possibilities that could not be confirmed by observation, somewhere in the statistical noise of extinction data and the infrared surveys of nearby space. The ghost of our sun's dark twin continues to haunt the intersection between paleontology and astronomy, a reminder that the most elegant explanations do not always correspond to reality. At the very edge of the sun's gravitational influence, far beyond the orbits of the known planets, a stellar companion could maintain a distant presence without disrupting the delicate orbital mechanics that govern our familiar solar system. Wide binary star systems throughout the galaxy demonstrate that stellar partnerships can exist across vast distances, with companion stars following orbits measured in light years rather than astronomical units. These loosely bound systems challenge conventional notions of what constitutes a binary arrangement, extending stellar relationships across interstellar scales that dwarf planetary distances. A hypothetical solar companion following such a distant orbit would take millions of years to complete a single revolution around the Sun. The orbital period would stretch beyond the timescales of human civilization, beyond the rise and fall of ice ages, even beyond the evolutionary emergence of complex multicellular life on Earth. Each orbital cycle would span geological epochs, making the companion's gravitational influence so gradual as to be nearly imperceptible across human timescales, yet potentially significant over the deep history of the solar system. The mathematics of such extreme orbits pushes the boundaries of gravitational stability. At distances approaching 1 light-year from the Sun, a stellar companion would orbit at the very edge of our star's gravitational reach, where the tidal forces from nearby stars and passing molecular clouds could easily disrupt the tenuous gravitational bond. The orbital velocity at such distances would be measured in mere kilometers per hour, slower than highway traffic, making the system vulnerable to even minor gravitational perturbations from the galactic environment. For a wide binary companion to have survived since the solar system's formation 4.5 billion years ago, it would need to occupy a remarkably stable orbital configuration. Computer simulations suggest that only certain combinations of orbital eccentricity, inclination, and distance could resist disruption by the complex gravitational environment of the galaxy. The companion would need to follow a nearly circular path to avoid close approaches that might destabilize planetary orbits, yet maintain sufficient separation to avoid tidal stripping during encounters with other stars. The gravitational influence of such a distant companion would manifest itself most clearly in the realm of the Oort Cloud, that vast spherical shell of comets that surrounds the solar system at distances of 50,000 to 100,000 astronomical units. A stellar companion orbiting within or beyond this region would gradually perturb comet orbits over millions of years, potentially increasing the rate at which long-period comets fall inward toward the inner solar system. The effect would be subtle but cumulative, building up over cosmic timescales to produce detectable changes in the statistics of comet arrivals. The search for wide binary companions has become increasingly sophisticated as astronomical surveys map ever fainter stars in the Sun's neighborhood. Modern catalogues contain precise positions and proper motions for millions of stars within several hundred light-years, allowing astronomers to identify objects that share the Sun's motion through space. A genuine stellar companion would display the same velocity vector as our solar system, moving in parallel through the galaxy despite its enormous separation. Infrared astronomy has proven particularly valuable in this search, since cool red dwarf stars and brown dwarfs emit most of their energy at wavelengths longer than visible light. The Spitzer Space Telescope, the Herschel Observatory, and the Wide Field Infrared Survey Explorer have systematically catalogued thermal emission from objects throughout the solar neighborhood, creating an unprecedented census of the galaxy's dimmest stellar populations. If a brown dwarf companion lurks in the outer darkness, these surveys should have detected its faint infrared glow. The absence of obvious candidates in comprehensive sky surveys has led astronomers to consider increasingly exotic possibilities for a solar companion. Perhaps our stellar twin exists as a particularly dim brown dwarf, radiating so little energy that it remains below current detection thresholds. Or perhaps it follows an orbit inclined at a steep angle to the galactic plane, placing it in regions of sky that have received less intensive scrutiny. The search continues with each new generation of more sensitive instruments. Some astronomers proposed that a wide binary companion might explain subtle anomalies in the orbits of distant solar system objects. The dwarf planet Sedna follows an extremely elongated path that carries it from roughly 76 astronomical units at closest approach to nearly 1,000 astronomical units at its most distant point. This orbit appears gravitationally isolated from the known planets, suggesting the influence of an as-yet undiscovered massive object in the outer solar system. Could Sedna's peculiar orbit reflect the gravitational sculpting of a distant stellar companion? The recent discovery of additional trans-Neptunian objects with similarly detached orbits has strengthened the case for unknown gravitational influences in the outer solar system. These distant worlds seem to cluster in orbital orientations that might reflect shepherding by a massive, unseen object. However, the proposed perturbing body, often called Planet 9, would need to be roughly Neptune-sized and orbit at hundreds of astronomical units, making it a planetary companion rather than a stellar one. The distinction between planetary and stellar companions becomes blurred in the realm of brown dwarfs. Those failed stars with masses between roughly 13 and 80 times that of Jupiter. The most massive brown dwarfs approach the lower limit of stellar mass, burning deuterium in their cores and radiating modest amounts of heat from gravitational contraction. The least massive brown dwarfs overlap with the largest possible planets, creating a continuous spectrum of objects that challenge traditional classification schemes. If our solar system harbours a brown dwarf companion, it would represent one of the nearest such objects to Earth, making it an invaluable laboratory for studying the physics of failed stellar ignition. Brown dwarfs cool gradually over billions of years, their surface temperatures dropping from thousands of degrees in youth to barely above room temperature in old age. A primordial brown dwarf companion would now glow with the heat of its own slow contraction, potentially detectable by future infrared telescopes with sufficient sensitivity. The orbital dynamics of brown dwarf companions present their own unique challenges and opportunities. Unlike true stars, brown dwarfs possess planetary-scale magnetic fields that could interact with the solar wind and heliosphere in ways that might be detectable from Earth. Radio emissions from brown dwarf magnetospheres have been observed in isolated objects, suggesting that a solar companion might announce its presence through periodic radio signals as it rotates. The gravitational influence of a wide binary companion would also affect the long-term evolution of planetary orbits in ways that might be detectable through precise astronomical measurements. Over millions of years, even weak perturbations could cause measurable changes in orbital elements, creating signatures that careful observation might eventually reveal. The accumulation of tiny gravitational effects over cosmic timescales demonstrates how patience and precision can uncover even the most subtle astronomical phenomena. Only took 4 billion years for our solar system to settle into its current configuration, with or without the influence of a distant stellar companion. The question of our sun's solitude continues to motivate astronomical searches that push the boundaries of observational capability. Each negative result narrows the range of possibilities while the mystery persists, reminding us that our solar system may still harbour secrets hiding in the cosmic darkness beyond the reach of current technology. The wide binary stars continue their patient orbits throughout the galaxy. Stellar partners separated by light years yet bound by gravity's inexorable pull. Whether our Sun participates in such a distant relationship remains unknown, though the search continues with each advance in astronomical instrumentation and data analysis techniques across the vast expanses of the galaxy. Astronomers have begun to practice a form of gravitational archaeology, searching through the subtle motions and chemical signatures of nearby stars for clues about our Sun's lost stellar siblings. The technique relies on the fundamental principle that stars born from the same molecular cloud should share similar compositions and velocities, carrying the chemical fingerprints of their common birthplace through billions of years of galactic wandering, like forensic investigators examining trace evidence. Stellar archaeologists analyze the spectra of nearby stars for isotopic ratios and elemental abundances that might reveal family relationships hidden by cosmic time. The Sun's chemical composition tells a story of stellar generations that preceded its birth. Heavy elements like carbon, oxygen, and iron, the building blocks of rocky planets and biological chemistry, were forged in the nuclear furnaces of massive stars that exploded as supernovae billions of years ago. These stellar deaths enrich the interstellar medium with the raw materials necessary for second-generation star formation, creating the chemical conditions that would eventually allow the emergence of terrestrial worlds and carbon-based life. Spectroscopic analysis reveals that our Sun contains a mixture of elements consistent with formation in a molecular cloud that had been enriched by multiple generations of stellar nuclear synthesis. The ratios of different isotopes, atoms with the same number of protons but different numbers of neutrons, provide particularly sensitive indicators of the stellar environment in which our solar system formed. Variations in isotopic composition can reveal whether stars originated in the same stellar nursery or formed under different galactic conditions. The search for solar siblings has identified several candidate stars that might have shared our Sun's birthplace. These stellar cousins display chemical compositions remarkably similar to our own star, suggesting they condensed from the same giant molecular cloud roughly 4.5 billion years ago. The most promising candidate, known as HD 162826, lies about 110 light-years away in the constellation Hercules, and shows isotopic signatures that match those of our Sun with extraordinary precision. Yet finding stars with similar chemical compositions represents only the first step in stellar archaeology. To confirm genuine sibling relationships, astronomers must also demonstrate that candidate stars followed similar paths through the galaxy's gravitational field over billions of years. This requires reconstructing stellar orbits backward through cosmic time, accounting for the complex gravitational influences of spiral arms, molecular clouds, and close encounters with other stars that have gradually dispersed the original stellar cluster. The challenge of stellar orbit reconstruction pushes the limits of galactic dynamics calculations. Computer simulations must model the gravitational effects of the galaxy's rotating spiral pattern, the vertical oscillations of stars above and below the galactic plane, and the chaotic interactions that occur when stellar systems pass close to giant molecular clouds. Even small uncertainties in initial conditions can lead to dramatically different orbital histories, making definitive sibling identification extremely difficult. The European Space Agency's Gaia mission has revolutionized the field of stellar archaeology by providing unprecedented precise measurements of stellar positions, distances, and velocities. This space-based observatory has mapped the three-dimensional motions of over 1 billion stars, creating a comprehensive census of stellar kinematics that extends throughout the galaxy's disk. The precision of Gaia's measurements allows astronomers to trace stellar orbits with accuracy sufficient to identify genuine dynamical families among the galaxy's stellar population. Gaia's data reveals that the galaxy's stellar population contains numerous moving groups, collections of stars that share similar space velocities and may represent the dispersed remnants of ancient star clusters. These kinematic families provide natural laboratories for studying stellar formation and evolution, since their members formed under similar conditions but have since evolved as isolated systems. Some moving groups contain dozens of stars spread across hundreds of light years, testimony to the gradual dissolution of gravitationally bound clusters over cosmic time. The process of stellar cluster dispersal unfolds through mechanisms both subtle and dramatic. Gravitational encounters with giant molecular clouds can strip away the least tightly bound members of stellar associations, while tidal forces from the galaxy's spiral arms gradually stretch clusters until they lose their gravitational cohesion. Even internal dynamics play a role. As massive stars evolve rapidly and explode as supernovae, removing significant mass from cluster cores and allowing remaining members to escape into the galactic field. The timescale for complete cluster dissolution depends sensitively on the initial mass and density of the stellar association. Dense globular clusters can remain gravitationally bound for many billions of years, while loose stellar associations may disperse within a few tens of millions of years. Our Sun likely formed in an intermediate environment, dense enough to promote binary star formation through gravitational capture, but not so compact as to prevent eventual dispersal through galactic tidal forces. Chemical tagging represents the most powerful technique for identifying stellar siblings among the galaxy's vast population. This method relies on the fact that stars formed from the same molecular cloud should display identical abundances of rare isotopes and trace elements, creating unique chemical signatures that persist throughout stellar lifetimes. Advanced spectrographs can measure elemental abundances with precisions approaching 1 part in 1,000, providing chemical fingerprints sensitive enough to distinguish between stars formed in different galactic environments. The application of chemical tagging to solar sibling searches has revealed the complexity of galactic chemical evolution. Even stars that appear to be siblings based on kinematics sometimes display subtle chemical differences that suggest formation in different regions of the same molecular cloud. The interstellar medium exhibits chemical gradients and inhomogeneities that can create detectable variations in stellar composition over relatively small spatial scales, complicating efforts to identify genuine stellar families. Modern surveys combine kinematic and chemical information to create comprehensive stellar genealogies that trace the formation history of the galaxy's disk population. Projects like Gala and Apogee have obtained high-resolution spectra for hundreds of thousands of stars, measuring precise abundances for dozens of different elements in each stellar atmosphere. These chemical census projects reveal that stellar formation has proceeded through multiple distinct episodes, each characterized by different patterns of galactic chemical enrichment. The search for our Sun's stellar siblings has broader implications for understanding the formation of planetary systems and the emergence of life. If our solar system formed within a dense stellar cluster, the gravitational environment during planetary formation would have been dramatically different from current conditions. Close encounters with neighboring stars could have disrupted the early solar nebula, affecting the efficiency of planetary accretion and the final orbital architecture of the solar system. Some astronomers propose that stellar clusters provide ideal environments for the exchange of biological material between planetary systems. During the dense phase of cluster evolution, when stars orbit within a few light-years of each other, asteroid and comet impacts could potentially transfer rocks and any microorganisms they contain, between different solar systems. This process of lithopanspermia might allow life to spread throughout stellar clusters, creating biological connections between planetary systems separated by interstellar distances. The discovery that our Sun likely possesses stellar siblings distributed throughout the galaxy raises profound questions about the uniqueness of Earth's biosphere. If similar planetary systems formed around chemically identical stars, they might have developed comparable evolutionary environments and possibly even analogous forms of life. The search for solar siblings thus becomes intertwined with astrobiology and the broader quest to understand whether life represents a common outcome of planetary evolution or a rare accident of cosmic chemistry. Only took billions of years for gravitational forces to scatter our Sun's stellar family across the galaxy's spiral arms, leaving behind only subtle chemical and kinematic clues to their common origin. The techniques of stellar archaeology continue to improve with each new generation of instruments and data analysis methods, gradually revealing the hidden connections that link our solar system to its stellar past and the broader story of galactic evolution. In the outermost reaches of the solar system, far beyond the orbits of the giant planets, lies a vast spherical shell of icy bodies that marks the boundary between our Sun's gravitational domain and the interstellar void. The Oort Cloud, named after the Dutch astronomer who first proposed its existence, contains perhaps 1 trillion individual comets distributed throughout a region extending from 20,000 to 100,000 astronomical units from the Sun. This distant realm represents the final frontier of solar influence, where our star's gravity barely exceeds the competing tidal forces of nearby stars and the galaxy itself. The comets that populate this remote region exist in a state of deep freeze that has persisted since the solar system's formation 4.5 billion years ago. At such enormous distances from the Sun, temperatures hover just a few degrees above absolute zero, creating conditions where water, carbon dioxide, and methane remain permanently frozen. These pristine icy bodies preserve the original chemistry of the solar nebula, serving as time capsules that contain samples of the raw materials from which planets formed during the earliest epochs of solar system history. The structure of the Oort Cloud reflects the complex gravitational processes that shaped the outer solar system during its chaotic youth. Computer simulations suggest that most Oort Cloud comets originated much closer to the Sun, in the region now occupied by the giant planets. Gravitational encounters with Jupiter, Saturn, Uranus, and Neptune gradually scattered these primitive bodies outward, launching them on highly elongated orbits that carry them to the very edge of solar gravitational influence. The process unfolded over hundreds of millions of years as the giant planets slowly migrated to their current orbital positions. The Oort Cloud's spherical geometry distinguishes it from the flattened disk structure that characterizes the inner solar system. While planets and asteroids orbit in roughly the same plane inherited from the original solar nebula, Oort Cloud comets follow orbits oriented randomly in three-dimensional space. This isotropic distribution results from the gradual randomization of orbital inclinations by stellar perturbations over billions of years. The galaxy's gravitational field and encounters with passing stars have slowly stirred the cloud into its current spherical configuration. Within this vast population of dormant comets, subtle gravitational influences occasionally send individual bodies on journeys toward the inner solar system. The perturbations arise from various sources: the tidal field of the galaxy, close approaches by neighboring stars, or passage through giant molecular clouds, each capable of altering comet orbits just enough to initiate their spectacular transformation from invisible ice balls to the glowing apparitions that grace Earth's skies. The process by which these perturbations select individual comets for inward journeys remains one of the solar system's most elegant examples of gravitational randomness. The tidal field of the galaxy itself provides a constant, gentle influence on Oort Cloud dynamics. As the solar system orbits the galactic center, it experiences differential gravitational forces that tend to stretch the cloud in the direction of galactic rotation. This galactic tide creates a subtle but persistent torque that gradually modifies comet orbits over millions of years. The effect is strongest for the most distant members of the cloud, where solar gravity becomes comparable in strength to the galaxy's tidal forces. Passing stars represent more dramatic but less frequent sources of Oort Cloud perturbation. Computer models suggest that roughly once every million years, a neighboring star approaches within 1 or 2 light-years of the solar system, close enough to significantly disrupt the orbits of the most loosely bound comets. These stellar encounters can trigger cometary showers that increase the rate of new comet arrivals in the inner solar system by factors of 10 or more. Though the effects unfold over timescales of hundreds of thousands of years, the most severe disruptions occur when the solar system passes through giant molecular clouds, those vast regions of dense interstellar gas and dust where new stars are born. Such encounters happen roughly every few tens of millions of years as the Sun follows its orbit around the galaxy. The increased density of matter within molecular clouds enhances their gravitational influence, potentially stripping away the outermost regions of the Oort cloud and sending massive numbers of comets tumbling toward the inner planets. If our Sun possessed a distant stellar companion, its gravitational influence would add another layer of complexity to Oort cloud dynamics. Depending on the companion's mass and orbital characteristics, it could either stabilize or destabilize comet orbits through resonant interactions that build up over millions of orbital periods. A companion following a highly eccentric orbit might create periodic disturbances that correlate with geological or biological events on Earth. Though no such correlation has been convincingly demonstrated in the astronomical or paleontological record, the search for signatures of binary companion influence in Oort cloud structure has motivated detailed studies of long-period comet statistics. Astronomers examine the orbital orientations and periods of newly discovered comets for patterns that might reveal the gravitational influence of an unseen stellar companion. The absence of clear periodicities or directional biases in comet arrival directions provides constraints on the properties of any hypothetical binary partner. Though the statistical sample remains too small for definitive conclusions, modern surveys have catalogued several thousand long-period comets with orbital periods ranging from hundreds to millions of years. These objects represent only a tiny fraction of the total Oort cloud population, since most comets remain too faint to detect until they approach within a few astronomical units of the Sun. The observed sample nonetheless provides valuable insights into the structure and evolution of the cloud, revealing the complex interplay between solar gravity, galactic tides, and stellar perturbations that governs comet dynamics. The composition of Oort cloud comets offers clues about the conditions that prevailed during the early solar system's formation. Spectroscopic analysis of comet atmospheres reveals the presence of water, carbon monoxide, carbon dioxide, methanol, and dozens of other compounds that condensed from the cooling solar nebula. The isotopic ratios of these molecules sometimes differ from those found in terrestrial materials, suggesting that comets formed in regions with different temperatures and pressures than the inner planets. Some Oort cloud comets display unusual compositional signatures that hint at exotic formation environments. Objects with anomalously high ratios of heavy hydrogen to normal hydrogen may have incorporated interstellar ice grains that predated the solar system's formation. These pristine materials survived the violent processes of stellar birth to become incorporated into comet nuclei, creating chemical time capsules that preserve samples of the galaxy's ancient interstellar medium. The study of Oort Cloud dynamics has implications that extend far beyond our own solar system. Similar cometary populations likely surround most stars throughout the galaxy, creating vast reservoirs of volatile materials that could potentially be disturbed by gravitational interactions. In binary star systems, the complex orbital mechanics of stellar companions might create dramatically different patterns of cometary flux, with implications for the bombardment histories of any planets that orbit such systems. The role of cometary impacts in Earth's geological and biological history remains an active area of research. While asteroid impacts receive more attention due to their association with mass extinction events, comet impacts may have played equally important roles in delivering water and organic compounds to the early Earth. The late heavy bombardment that occurred roughly 4 billion years ago involved impacts from both asteroids and comets, creating the chemical conditions necessary for the emergence of life. Only took billions of years for the Oort Cloud to settle into its current configuration, a spherical shell of pristine ice that preserves the chemical memory of the solar system's birth, while occasionally releasing individual messengers that carry tales of the cosmic deep freeze to warmer inner worlds. Whether the gravitational influence of a distant stellar companion has shaped this distant realm remains unknown, though the cloud's structure and dynamics continue to provide constraints on our understanding of the solar system's hidden architecture. In the dim borderlands between planets and stars, a population of failed stellar objects drifts through space in gravitational limbo. Brown dwarfs occupy the mass range between the largest possible planets and the smallest true stars, typically containing between 13 and 80 times the mass of Jupiter but lacking sufficient nuclear fuel to sustain the hydrogen fusion that powers genuine stars. These cosmic misfits glow with the heat of their own slow gravitational contraction, cooling gradually over billions of years from surface temperatures of thousands of degrees to barely above room temperature in old age. The discovery of brown dwarfs has revolutionized astronomers' understanding of stellar formation and the lower limits of stellar ignition. During the 1990s, infrared surveys began detecting objects too cool and dim to be ordinary stars yet too massive to be planets. These finds confirmed theoretical predictions that star formation should produce a continuum of masses, including objects that fall short of the minimum requirements for sustained nuclear fusion. Brown dwarfs represent nature's failed attempts at stellar creation, cosmic near misses that illuminate the boundary between stellar and planetary physics. The internal structure of brown dwarfs differs fundamentally from both planets and stars, creating unique physical conditions found nowhere else in the universe. Unlike planets, brown dwarfs generate their own heat through gravitational compression, slowly radiating away the energy released during their initial collapse from the interstellar medium. Unlike stars, they lack the central temperatures necessary to fuse hydrogen nuclei, though the most massive brown dwarfs can burn deuterium, heavy hydrogen, for a few tens of millions of years before exhausting this limited fuel supply. The atmospheric properties of brown dwarfs create weather patterns and chemical processes unlike anything found in the solar system. At surface temperatures ranging from 2000 degrees in young objects to a few hundred degrees in ancient ones, brown dwarf atmospheres host exotic cloud formations composed of silicate particles, liquid iron droplets, and complex organic compounds. These atmospheric layers create intricate patterns of heat circulation and chemical transport that astronomers are only beginning to understand through detailed spectroscopic observations. If our solar system harbours a brown dwarf companion, it would likely exist as one of the coolest, oldest members of this exotic stellar class. After 4.5 billion years of cooling, a primordial brown dwarf would have surface temperatures comparable to those found in kitchen ovens, radiating primarily in the far infrared portion of the electromagnetic spectrum. Such an object would be extraordinarily difficult to detect with current technology, requiring specialized infrared telescopes sensitive to wavelengths longer than those accessible to most astronomical instruments. The search for brown dwarf companions has intensified with each advance in infrared astronomy capabilities. Space-based observatories like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer have mapped thermal emission from objects throughout the solar neighborhood, creating comprehensive catalogues of cool stellar remnants and failed stars. These surveys have discovered hundreds of brown dwarfs within a few dozen light-years of Earth, revealing a population density that suggests such objects may be nearly as common as ordinary stars. The orbital dynamics of brown dwarf companions present unique challenges for astronomical detection. Unlike massive stars that create obvious gravitational perturbations in their host systems, brown dwarfs exert relatively subtle influences that might be detectable only through precise long-term observations. A brown dwarf orbiting at distances of hundreds or thousands of astronomical units would produce gravitational effects so small that decades of monitoring might be required to confirm its presence through astrometric measurements of stellar wobble. Magnetic field interactions provide another potential signature of brown dwarf companions. These objects generate surprisingly strong magnetic fields through internal convection processes, creating magnetospheres that can extend far beyond their physical surfaces. If a brown dwarf companion exists within the heliosphere, the region dominated by the solar wind, it might produce detectable radio emissions as charged particles from the Sun interact with the companion's magnetic field structure. The rotation periods of brown dwarfs offer additional opportunities for detection through photometric monitoring. These objects typically rotate much faster than ordinary stars, with periods ranging from a few hours to a few days. Surface features such as cloud patterns and magnetic storms create brightness variations that repeat with the rotation period, allowing astronomers to measure spin rates through careful light curve analysis. A brown dwarf companion might reveal its presence through periodic dimming as it rotates and different hemispheres face Earth. The chemical composition of brown dwarfs reflects their formation environment and subsequent evolution in ways that could provide clues about their origins. Spectroscopic analysis reveals the presence of water vapor, methane, carbon monoxide, and other molecules that form in the cool atmospheres of these objects. The relative abundances of different species depend on temperature, pressure, and the availability of various elements, creating chemical fingerprints that encode information about formation conditions and thermal history. Some brown dwarfs display atmospheric compositions that suggest formation in environments very different from typical stellar nurseries. Objects with unusual carbon to oxygen ratios or enhanced abundances of heavy elements might have formed through gravitational collapse of material enriched by nearby supernovae or planetary nebulae. Others show evidence of atmospheric mixing processes that bring material from deep interiors to observable surface layers, providing windows into the internal chemistry of these exotic objects. The possibility of planetary systems around brown dwarfs has captured the imagination of astronomers and astrobiologists studying alternative pathways to planetary formation. Several brown dwarfs are known to host disk structures that might represent sites of ongoing planet formation, though the low luminosity of these objects creates challenging conditions for the development of habitable worlds. Planets orbiting brown dwarfs would need to orbit very close to their host to receive sufficient heat for liquid water, placing them within tidal locking distance where one hemisphere faces the brown dwarf permanently. Recent discoveries have revealed brown dwarfs that exist in binary partnerships with each other, creating systems where two failed stars orbit their common center of mass in gravitational partnership. These brown dwarf binaries provide natural laboratories for studying the physics of substellar objects, since the orbital parameters can be measured precisely through eclipse timing and spectroscopic analysis. Some of these systems display orbital periods of just a few hours, with the two brown dwarfs nearly touching as they whirl around each other in cosmic figure-8 patterns. The formation mechanisms that produce brown dwarfs remain subjects of active research and theoretical modelling. Some brown dwarfs may form through the same processes that create ordinary stars, but in environments where insufficient material is available to reach the stellar mass threshold. Others might represent planets that were ejected from their parent systems during chaotic early phases of planetary formation, subsequently growing through accretion of interstellar material to reach brown dwarf masses. The distinction between the most massive planets and the least massive brown dwarfs has become increasingly blurred as astronomers discover objects that challenge traditional classification schemes. Free-floating planetary mass objects, brown dwarfs with masses comparable to Jupiter but unbound to any host star, exist in significant numbers throughout the galaxy. These cosmic orphans may represent the low-mass tail of the brown dwarf population or planets that were gravitationally ejected from their birth systems during violent early evolution. The thermal evolution of brown dwarfs follows predictable patterns that allow astronomers to estimate ages and masses through careful photometric and spectroscopic observations. Young brown dwarfs shine brightly in infrared light as they radiate the heat generated during their initial gravitational collapse. Over hundreds of millions of years, they cool and dim according to well-understood physical laws, their surface temperatures dropping as internal heat gradually leaks away into space. Only took billions of years for any hypothetical brown dwarf companion to cool from stellar temperatures to planetary ones, transforming from a glowing ember visible in telescopes to a dim infrared source detectable only by the most sensitive instruments. The search continues as infrared astronomy pushes toward ever greater sensitivity, gradually expanding the volume of space within which such objects could be detected and characterized through their faint thermal emission. The story of our Sun's solitude begins not in the emptiness of interstellar space, but in the crowded stellar nurseries where most stars spend their formative years. Computer simulations of stellar formation suggest that our Sun likely condensed from a giant molecular cloud alongside hundreds or thousands of sibling stars, all born within a few million years of each other from the same reservoir of gas and dust. This stellar cluster would have resembled the Pleiades or the Orion Nebula, dense associations of young stars packed into regions just a few light-years across, where gravitational interactions and stellar winds created a chaotic but creative environment. During its cluster phase, our solar system would have experienced conditions dramatically different from the serene isolation it enjoys today. Young stars in dense clusters orbit within a few light-years of their neighbours, close enough for gravitational encounters that can alter planetary orbits, strip away outer planets, or even exchange planetary systems between different stars. The early Sun might have passed within 1 or 2 astronomical units of neighbouring stars, closer than the current distance to Mars, creating gravitational perturbations that could have reshaped the entire architecture of the nascent solar system. The evidence for our Sun's cluster origins comes from multiple lines of astronomical investigation. Chemical analysis reveals that our star formed from material enriched by multiple generations of stellar nucleosynthesis, suggesting birth within a region where massive stars had already lived, died, and expelled their nuclear products into the surrounding medium. The isotopic composition of meteorites provides additional clues, including short-lived radioactive elements that could only have been deposited by nearby supernova explosions during the solar system's formation epoch. Stellar clusters represent factories for binary star formation, environments where gravitational encounters can capture unbound stars into orbital partnerships or exchange companions between different stellar systems. In the dense cores of young clusters, three-body interactions create temporary gravitational arrangements that sometimes resolve into stable binary pairs. A single star like our early Sun, passing close to an existing binary system, might capture the less massive member while the original primary escapes into the cluster's general population. The timescales for cluster dispersal depend critically on the initial mass and density of the stellar association. Low-mass clusters with a few hundred members typically dissolve within 10 to 50 million years as internal gravitational interactions gradually accelerate individual stars beyond the cluster's escape velocity. More massive clusters can remain partially bound for hundreds of millions of years, though even these eventually succumb to the disruptive effects of galactic tidal forces and encounters with giant molecular clouds. The dispersal process unfolds through mechanisms both internal and external to the cluster. Mass loss from evolving stars reduces the total gravitational binding energy, allowing less tightly bound members to escape more easily. Stellar winds and supernova explosions create additional disruptions that can blow away significant fractions of the cluster's population. Meanwhile, external forces such as encounters with molecular clouds or passage through galactic spiral arms provide the final gravitational kicks that complete the dissolution process. Archaeological evidence for our Sun's cluster heritage has proven remarkably elusive despite decades of intensive searching. Astronomers have identified several moving groups of stars that share similar space velocities and might represent the dispersed remnants of ancient clusters, but none show the precise kinematic and chemical signatures expected from our Sun's birth environment. The lack of obvious solar siblings suggests either that the original cluster dispersed very completely, or that our current understanding of stellar formation in dense environments remains incomplete. The Hyades cluster, located about 150 light-years away in the constellation Taurus, provides an example of how stellar associations gradually dissolve over cosmic time. This cluster contains several hundred stars born roughly 600 million years ago, but its members now span a region more than 60 light-years across. Gravitational interactions have gradually stretched the cluster into an elongated stream of stars that will eventually merge with the galaxy's general stellar population, leaving no trace of their common origin except for subtle similarities in chemical composition and space motion. Recent advances in astrometry and spectroscopy have enabled searches for solar siblings among the galaxy's vast stellar population. The European Space Agency's Gaia mission has measured precise positions and velocities for over 1 billion stars, creating opportunities to identify kinematic families that might represent dispersed cluster remnants. Complementary spectroscopic surveys provide chemical abundances for hundreds of thousands of stars, allowing astronomers to search for the isotopic signatures that would identify genuine stellar siblings. Several candidate solar siblings have been identified through these comprehensive surveys, including stars with chemical compositions remarkably similar to our Sun's and space velocities consistent with a common origin roughly 4.5 billion years ago. The most promising candidate, designated HD 162826, displays isotopic ratios that match solar values within observational uncertainties and follows a galactic orbit that could have diverged from our solar system's path through gradual gravitational perturbations over billions of years. The confirmation of genuine solar siblings requires painstaking analysis that combines kinematic, chemical, and age information to rule out chance coincidences. Even stars with very similar properties might have formed in different molecular clouds that happen to possess comparable chemical compositions. The galaxy's complex patterns of star formation and chemical enrichment create backgrounds of stellar diversity that can mimic family relationships where none actually exist. The absence of a large population of easily identifiable solar siblings suggests that our Sun's birth cluster dispersed very completely, with individual members now scattered throughout the galaxy's disk. Computer simulations indicate that after 4.5 billion years of galactic evolution, the original cluster members might be separated by thousands of light years and show no obvious kinematic coherence. The search for these stellar relatives has become an exercise in galactic archaeology that pushes the limits of observational astronomy. The dynamics of stellar clusters provide natural mechanisms for binary star disruption that could explain our Sun's apparent solitude. Close encounters between single stars and binary systems can result in exchange reactions where the least massive star is ejected while the remaining two form a new binary pair. Alternatively, three-body interactions might disrupt binary systems entirely, leaving both components as single stars with modified orbital energies. Our Sun might have lost a binary companion through such processes during its cluster phase. The frequency of binary disruption in young clusters depends on stellar density, velocity dispersion, and the initial binary fraction among cluster members. Dense cluster cores create conditions where gravitational encounters occur frequently enough to significantly modify the binary population over timescales of a few million years. Even wide binary systems with separations of hundreds of astronomical units can be disrupted by close encounters with neighboring stars or by tidal forces from the cluster's gravitational field. The survival probability for binary systems in dense clusters decreases with increasing cluster membership and density, suggesting that our Sun's hypothetical companion would have faced challenging odds during its youth. Computer simulations indicate that only the most tightly bound binary pairs survive the chaotic environment of cluster cores, while wider systems are gradually stripped away through gravitational interactions with neighboring stars. The absence of a solar companion might simply reflect the statistical reality that most wide binaries do not survive cluster dispersal. Only took a few tens of millions of years for our Sun's birth cluster to dissolve completely, scattering its stellar children across the galaxy's spiral arms and erasing most traces of their common heritage. The cluster phase of stellar evolution represents a brief but crucial period when gravitational interactions determine which stars will travel through space as isolated wanderers and which will maintain stellar partnerships throughout their long journeys around the galactic center. The presence of a binary stellar companion would have fundamentally altered the gravitational architecture of our solar system, creating tidal forces and orbital perturbations that could have prevented the formation of stable, nearly circular planetary orbits that characterize our cosmic neighborhood today. In binary star systems throughout the galaxy, the gravitational influence of stellar companions creates complex dynamical environments where planetary formation follows different rules and produces exotic arrangements unknown in single-star systems. The delicate orbital mechanics that allowed Earth to maintain liquid water for billions of years might have been impossible in the presence of a second star. Tidal forces from a binary companion would have affected planetary formation from the earliest stages of solar system evolution, during the initial phases when microscopic dust grains were slowly aggregating into larger bodies. The differential gravitational pull of two stars could have created zones of enhanced or reduced particle density that channeled accretion into preferential locations. These tidal resonances might have prevented planet formation entirely in certain orbital regions, while concentrating material at distances that produce planetary arrangements very different from our current solar system. The mathematical description of tidal forces in binary systems reveals their profound influence on planetary orbital stability. A stellar companion exerts gravitational forces that vary with distance according to the inverse square law. But the difference between forces on opposite sides of an orbiting planet, the tidal force, varies as the inverse cube of separation. This means that tidal effects drop off rapidly with distance, but can become extremely strong when planetary orbits bring them close to either stellar component of a binary system. Computer simulations of planetary formation in binary environments demonstrate the complex interplay between stellar orbits, planetary accretion, and long-term orbital stability. Close binary systems with stellar separations comparable to the outer solar system create gravitational chaos that prevents the formation of stable planetary orbits beyond a few astronomical units from either star. Wide binary systems allow for planet formation around individual stellar components, but subject these planets to slow orbital evolution over millions of years as the binary orbit gradually changes due to galactic perturbations. The concept of habitable zones becomes significantly more complex in binary star systems, where the combined radiation from two stars creates temperature patterns that vary both spatially and temporally. Planets orbiting close binary systems might experience double sunsets and complex seasonal cycles as the two stars follow their orbital dance around each other. The gravitational perturbations from the secondary star could drive planetary orbits into eccentric configurations that produce extreme climate variations unsuitable for biological evolution. Circumbinary planets, worlds that orbit both stars of a binary system, follow gravitational paths of remarkable complexity that challenge traditional notions of planetary mechanics. These planets must maintain stable orbits despite the constantly changing gravitational field created by the binary stellar motion, threading gravitational needles through regions of stability surrounded by zones of chaotic dynamics. The few confirmed circumbinary planets discovered so far display orbital properties unlike anything found in single-star systems, with periods and eccentricities that reflect their complex dynamical heritage. The zone of gravitational stability around binary stars depends critically on the mass ratio and orbital characteristics of the stellar components. For planets orbiting individual stars in wide binary systems, stable orbits typically exist within about 1/3 of the binary separation distance. Closer to the companion star, gravitational perturbations destabilize planetary orbits over timescales ranging from thousands to millions of years. This constraint severely limits the volume of space available for stable planet formation in most binary configurations. The migration of giant planets, a process that played crucial roles in shaping our solar system's architecture, would have proceeded very differently in the presence of a binary companion. The gravitational torques that drive planetary migration through interaction with protoplanetary disk material become modified by the tidal field of the secondary star, potentially accelerating migration rates or driving planets into resonant configurations that do not exist in single-star systems. Jupiter's inward migration, which may have sculpted the asteroid belt and delivered water to the inner planets, might have proceeded to completion in a binary environment, leaving no terrestrial planets in habitable orbits. The asteroid belt, that collection of rocky debris between Mars and Jupiter that preserves samples of the solar system's earliest solid materials, owes its existence to gravitational resonances with Jupiter that prevented these fragments from accreting into a full-size planet. In a binary system, additional resonances created by the stellar companion could have either enhanced this grinding process or allowed complete planetary formation depending on the specific orbital parameters involved. The complex interplay between multiple gravitational sources creates possibilities for asteroid belt formation or destruction that remain largely unexplored by current theoretical models. The Kuiper belt and scattered disk populations that inhabit the outer solar system would have experienced dramatically different evolutionary histories in the presence of a stellar companion. These regions contain thousands of icy bodies that preserve information about the outer solar system's formation and early dynamical evolution. The orbital distribution of Kuiper belt objects reflects the influence of Neptune's migration and gravitational resonances that sculpted the outer planet's arrangement over hundreds of millions of years. A binary companion would have created additional resonances and migration pathways that could have completely altered this population structure. The late heavy bombardment, that period roughly 4 billion years ago when asteroid and comet impacts peaked throughout the inner solar system, might have been triggered by binary companion effects, rather than the planetary migration events favoured by current models. Gravitational perturbations from a stellar companion could have destabilized outer solar system bodies over extended periods, creating episodic bombardment that delivered water and organic compounds to the terrestrial planets at rates and times very different from those that actually occurred. The precise orbital mechanics that maintain Earth's stable climate depend on gravitational relationships between the Sun, Moon, and planets that could have been disrupted by additional stellar mass in the outer solar system. Earth's obliquity, the tilt of its rotation axis that creates seasonal cycles, varies slowly over timescales of tens of thousands of years due to gravitational torques from the Moon and planets. A binary companion would have introduced additional torques that could have driven larger obliquity variations, creating ice age cycles with different frequencies and intensities than those found in the geological record. The Moon's formation through a giant impact between early Earth and a Mars-sized planetesimal represents one of the most dramatic events in solar system history. The specific conditions that allowed this collision to occur, including the impactor's mass dissip, velocity, and angle of approach, might have been very different in a binary environment where additional gravitational perturbations affected the dynamics of planetary formation. The Moon's subsequent orbital evolution, including its gradual recession from Earth due to tidal friction, would have proceeded differently under the influence of a stellar companion's gravitational field. Planetary ring systems, such as those that encircle Saturn and the other giant planets, represent delicate gravitational structures that can be disrupted by external perturbations over geological timescales. The narrow gaps and complex structure of Saturn's rings result from gravitational resonances with moons that maintain precise orbital relationships over millions of years. A binary stellar companion would have introduced additional perturbations that could have prevented ring formation entirely, or created exotic ring architectures unlike anything observed in our current solar system. The formation of regular satellite systems around the giant planets, those families of moons that orbit in the same direction as planetary rotation and maintain nearly circular coplanar orbits, requires stable circumplanetary disks during the late stages of planetary formation. Binary companion effects could have disrupted these disks through tidal truncation or induced spiral density waves that prevented the orderly accretion process that created the Galilean satellites of Jupiter and the major moons of Saturn. The resulting satellite systems might have consisted primarily of captured irregular objects with chaotic orbital orientations. The dynamics of planetary rotation would have evolved differently under the influence of binary tidal forces. The Earth-Moon system's angular momentum and the gradual slowing of Earth's rotation through tidal friction represent consequences of our planet's specific formation history and subsequent gravitational interactions. A stellar companion could have created additional tidal torques that accelerated or decelerated planetary rotation rates. potentially affecting the development of magnetic fields that shield planetary atmospheres from stellar radiation. The long-term stability of planetary atmospheres depends on complex interactions between solar radiation, magnetic fields, and gravitational retention that could have been altered by binary companion effects. Venus lost its water through runaway greenhouse processes that might have been accelerated by enhanced stellar radiation from a binary system. Mars lost much of its atmosphere through solar wind stripping that could have proceeded differently under the influence of variable stellar radiation and magnetic field interactions in a binary environment. The chemical evolution of planetary atmospheres follows pathways determined by the balance between atmospheric escape processes and volatile delivery from impacts. In a binary system, both the impact rate and the stellar radiation environment could have differed significantly from single-star conditions, potentially preventing the development of oxygen-rich atmospheres like Earth's, or creating atmospheric compositions that have no analogues in our current solar system. Only took 4.5 billion years for our solar system to evolve its current stable configuration through gravitational processes that might have been impossible in the presence of a stellar companion. The absence of binary perturbations allowed for the gradual orbital evolution that created Earth's temperate climate, the Moon's stabilizing influence on obliquity cycles, and the asteroid belt's role as a source of water and organic compounds for the inner planets. The delicate gravitational balance that maintains this favorable arrangement represents one of the solar system's most remarkable features, a clockwork of orbital relationships that could easily have been disrupted by the presence of a second star. Among the galaxy's vast stellar population, red dwarf stars represent the most common and longest-lived members of the cosmic community. These small, cool stars burn hydrogen so slowly and efficiently that they can maintain steady nuclear fusion for hundreds of billions of years, lifespans that exceed the current age of the universe by factors of 10 or more. With masses ranging from about 8% to 60% that of our Sun, red dwarfs glow with surface temperatures between 2,500 and 4,000 degrees Kelvin, radiating primarily in infrared wavelengths that make them invisible to the naked eye despite their overwhelming numerical dominance. The statistical likelihood that our Sun might have formed with a red dwarf companion reflects the extraordinary abundance of these objects throughout galactic stellar populations. Recent surveys suggest that red dwarfs comprise roughly 75% of all stars in the galaxy, making them the default stellar type from which binary companions would most likely be drawn. If our solar system once harboured a stellar partner, probability alone suggests it would have been a small, dim, long-lived red dwarf rather than a more massive and conspicuous stellar type. The formation of red dwarf stars follows the same gravitational collapse processes that create larger stars, but with initial cloud masses too small to generate the central densities and temperatures required for vigorous nuclear burning. These modest stellar nurslings ignite nuclear fusion with barely enough gravitational pressure to sustain hydrogen burning, creating internal conditions that burn fuel so conservatively that red dwarfs remain essentially unchanged for cosmological timescales. A red dwarf born alongside our Sun would still be burning hydrogen today with virtually identical properties to those it possessed 4.5 billion years ago. The search for red dwarf companions has intensified as infrared surveys achieved the sensitivity required to detect these intrinsically faint objects at interstellar distances. Ground-based infrared telescopes and space-based observatories have systematically catalogued thermal emissions from objects throughout the solar neighbourhood, creating comprehensive databases that would contain any red dwarf orbiting within several light-years of our solar system. The absence of obvious candidates in these surveys places increasingly stringent constraints on the properties of any hypothetical stellar companion. Red dwarf binary systems throughout the galaxy demonstrate the gravitational stability that allows stellar partnerships to persist over cosmological timescales. Unlike more massive stars that evolve rapidly through giant phases and explosive endpoints, red dwarfs maintain constant mass and luminosity that preserve binary orbital relationships essentially unchanged throughout the age of the universe. A red dwarf companion to our Sun could have maintained a stable orbit since the solar system's formation without the mass loss or stellar evolution that disrupt many other types of binary systems. The orbital mechanics of red dwarf companions present unique advantages for long-term gravitational stability. The low mass of these objects creates relatively weak tidal forces that are less likely to disrupt planetary formation or destabilize existing planetary orbits over geological timescales. A red dwarf following a sufficiently distant orbit could exert gravitational influences so gentle that the inner solar system would remain essentially unaffected, while still providing detectable perturbations in the outer regions where comets and distant asteroids trace the boundaries of solar gravitational influence. The luminosity evolution of red dwarfs follows patterns dramatically different from solar-type stars, with implications for any planetary systems that might orbit these long-lived objects. While our Sun gradually brightens over billions of years as helium accumulates in its core, red dwarfs actually become slightly dimmer with age as their internal structure slowly adjusts to the depletion of hydrogen in central regions. This cooling trend means that planets orbiting red dwarfs experience gradually decreasing temperatures over cosmological timescales, creating evolutionary environments that select for different biological adaptations than Earth's warming climate. The magnetic activity of red dwarfs creates stellar environments that can be both more violent and more stable than those around solar-type stars. Many red dwarfs exhibit powerful flare activity that can increase their luminosity by factors of 10 or more during explosive magnetic reconnection events. These stellar tantrums release high-energy radiation and charged particles that could sterilize any nearby planets. Yet the same magnetic fields responsible for flaring also create stellar corona and winds that differ significantly from solar conditions. The rotation periods of red dwarfs span enormous ranges that reflect their formation conditions and subsequent magnetic evolution. Young red dwarfs can rotate in periods of hours, spinning so rapidly that centrifugal forces nearly overcome gravitational attraction at their equators. Over billions of years, magnetic braking gradually slows their rotation to periods of weeks or months. Though some ancient red dwarfs become tidally locked to close companions and maintain synchronous rotation throughout their extended lifetimes. The atmospheric properties of red dwarfs create unique spectroscopic signatures that enable precise measurements of their physical properties and chemical compositions. The cool surface temperatures of these objects allow molecules like titanium oxide and water vapor to exist in their photospheres, creating complex absorption features that encode information about temperature, pressure, and elemental abundances. These molecular signatures provide astronomers with detailed diagnostics for characterizing red dwarf properties and identifying chemically peculiar objects that might have unusual formation histories. The search for planets around red dwarf stars has revealed surprising diversity in the types of worlds that can form around these low-mass objects. Despite their modest luminosity, red dwarfs can support planetary systems with multiple worlds orbiting in complex gravitational configurations. Some red dwarf systems contain planets larger than Jupiter, demonstrating that efficient planetary formation can occur even around the galaxy's smallest and least luminous stars. The discovery of potentially habitable planets around nearby red dwarfs has revolutionized astrobiological thinking about the prospects for life throughout the galaxy. The habitability of planets around red dwarf stars depends on factors very different from those that determine Earth's temperate climate. The habitable zones around red dwarfs lie extremely close to their host stars, typically within a few percent of Earth's orbital distance from the Sun. Planets orbiting in these regions experience strong tidal forces that likely lock them in synchronous rotation, creating permanent day and night hemispheres separated by terminator zones where complex atmospheric circulation patterns might maintain temperate conditions. The stellar winds from red dwarf stars differ significantly from the solar wind that shapes our heliosphere and influences planetary magnetospheres. The combination of strong magnetic fields and slow rotation creates wind patterns that can be either much stronger or much weaker than solar conditions. Depending on the specific properties of individual red dwarf objects, these variations in stellar wind strength affect the evolution of planetary atmospheres and the extent of stellar influence in the outer regions of planetary systems. The chemical composition of red dwarf atmospheres often reflects the galactic environment in which these stars formed, with older objects showing lower abundances of heavy elements than younger red dwarfs born from material enriched by successive generations of stellar nuclear synthesis. This metallicity dependence affects both the efficiency of planetary formation and the types of worlds that can form, creating correlations between stellar age, chemical composition, and planetary system architecture that provide insights into galactic chemical evolution. The binary fraction among red dwarf stars appears to be somewhat lower than that observed for more massive stellar types, though the statistics remain uncertain due to the difficulty of detecting close red dwarf companions round objects that are already intrinsically faint. Wide binary red dwarf systems do exist throughout the galaxy, demonstrating that gravitational capture or fragmentation during formation can create red dwarf partnerships that persist over cosmological timescales despite the weak gravitational binding energies involved. The astrometric signatures of red dwarf companions would be extremely subtle due to their low masses, requiring precision measurements that push the limits of current observational capabilities. The gravitational wobble induced by a red dwarf partner would produce positional shifts measured in microarc seconds, angular scales thousands of times smaller than the resolution of ground-based telescopes. Space-based astrometry missions like Gaia represent the current state of the art for such measurements. Though even these sophisticated instruments might not achieve sufficient precision to detect distant red dwarf companions around nearby stars. Only took billions of years for red dwarf stars to establish themselves as the galaxy's dominant stellar population, quiet nuclear furnaces that will continue burning long after more massive stars have exhausted their fuel and faded to white dwarf remnants. Whether our Sun shares its journey through space with such a diminutive companion remains one of astronomy's unsolved puzzles. Though the statistical prevalence of red dwarfs makes them prime candidates for any undiscovered stellar partnership in our cosmic neighborhood, the immense timescales of galactic evolution ensure that even the most stable stellar partnerships face gradual dissolution as gravitational interactions slowly pull binary companions apart over billions of years. The galaxy operates as a vast gravitational environment where countless stars, molecular clouds, and dark matter concentrations exert subtle but persistent influences on stellar motions. These accumulated perturbations gradually modify binary orbits through processes so slow that individual human lifetimes represent negligible fractions of the timescales involved, yet so inexorable that they eventually separate stellar partners that have travelled together since their birth in ancient molecular clouds. The mechanism of stellar separation begins with differential galactic orbits that arise when binary companions follow slightly different paths around the galaxy's centre of mass. The Sun completes one galactic orbit roughly every 220 million years, but this orbital period depends sensitively on the total mass distribution within the solar circle and the specific trajectory followed through regions of varying stellar density. A binary companion orbiting at distances of light years from our Sun would experience slightly different galactic tidal forces, gradually developing orbital velocity differences that accumulate over multiple galactic revolutions. Encounters with giant molecular clouds represent one of the most dramatic mechanisms for binary disruption over cosmic timescales. These vast repositories of star-forming material contain masses equivalent to millions of suns distributed throughout regions spanning hundreds of light years. When the solar system passes through or near such clouds, events that occur roughly every few tens of millions of years, the enhanced gravitational field can preferentially accelerate one member of a wide binary system, providing the velocity difference needed to break gravitational bonds that have persisted for billions of years. The statistical frequency of close stellar encounters increases gradually as the galaxy ages and stellar orbits become randomized through gravitational interactions. During the early phases of galactic evolution, most stars remained in the dense stellar associations where they formed, creating environments with high encounter rates that rapidly disrupted weakly bound binary systems. As stellar clusters dispersed and the galaxy settled into its current configuration, encounter rates decreased, allowing stable binary systems to survive for longer periods before experiencing disruptive interactions. Computer simulations of galactic dynamics reveal the complex interplay between stellar orbits, molecular cloud encounters, and binary evolution that determines which stellar partnerships survive over cosmological timescales. Wide binary systems with separations exceeding 10,000 astronomical units rarely survive more than a few billion years in the galactic disk environment, while closer binaries with separations measured in hundreds or thousands of astronomical units can persist for the full age of the galaxy under favorable conditions. The role of dark matter in binary evolution represents an active area of theoretical investigation that could significantly affect our understanding of stellar separation mechanisms. The galaxy's dark matter halo contains roughly 5 times more mass than all visible stars and gas combined, creating a gravitational environment that influences stellar orbits through mechanisms that remain poorly understood. Dark matter substructures, clumps and streams within the galactic halo, might create gravitational perturbations capable of disrupting binary systems through processes that do not involve conventional astronomical objects. The gradual expansion of binary orbits through gravitational wave radiation represents another mechanism that can lead to stellar separation over extremely long timescales. While this effect is negligible for most stellar binary systems, it becomes significant for the closest binaries where orbital periods are measured in hours or days. The energy radiated away as gravitational waves causes these systems to spiral inward rather than outward. But the same physical processes can work in reverse when external perturbations add energy to binary orbits and cause gradual expansion over cosmic time. The observational signatures of recently separated binary systems should be detectable through precise measurements of stellar kinematics and chemical compositions. Former binary companions would share similar space velocities and elemental abundances inherited from their common formation environment, creating kinematic families that could be identified through comprehensive surveys of stellar proper motions and radial velocities. The discovery of such families would provide direct evidence for binary disruption processes and constrain models of galactic evolution. The search for the Sun's hypothetical former companion has motivated studies of nearby stars with kinematics and chemistry similar to our solar system. Several candidate objects have been identified through spectroscopic surveys that measure detailed elemental abundances. But confirming genuine binary relationships requires ruling out alternative explanations such as formation in similar galactic environments or chance chemical coincidences. The statistical challenge of identifying true former companions among the vast stellar population of the galactic disk remains formidable. The timescales for binary separation depend critically on the initial orbital characteristics and the subsequent galactic environment encountered over billions of years. Binary systems with circular orbits and favorable orientations relative to galactic tidal forces can survive much longer than eccentric systems that experience large variations in separation distance. The chaotic nature of galactic dynamics means that even small differences in initial conditions can lead to dramatically different evolutionary outcomes over cosmic timescales. The fate of separated stellar companions depends on their masses and the velocities they acquire during the disruption process. Low-mass red dwarf stars might receive relatively small velocity kicks that leave them bound to the galaxy but following orbits very different from their original binary partner. More massive stars could acquire sufficient energy to escape the galactic disk entirely, becoming members of the stellar halo population that orbits at large distances from the galactic plane. The chemical evolution of the galaxy creates an additional layer of complexity in binary separation studies. As the interstellar medium from which stars form has changed significantly over the past 4.5 billion years, early generations of stars formed from material with low abundances of heavy elements, while more recent star formation has proceeded in environments enriched by successive generations of stellar nuclear synthesis. These chemical gradients can mimic the signatures expected from former binary companions and complicate efforts to identify genuine stellar siblings. The role of stellar evolution in binary separation becomes significant for systems containing intermediate or high-mass stars that undergo dramatic changes during their main sequence lifetimes. Mass loss through stellar winds or explosive events can reduce the gravitational binding energy of binary systems, making them more susceptible to disruption by external perturbations. The most massive stars typically evolve and die within a few tens of millions of years, potentially leaving behind remnants with very different gravitational properties than their main sequence progenitors. Modern astrometric surveys have achieved the precision necessary to detect the subtle kinematic signatures that might reveal recent binary separations. The European Space Agency's Gaia mission has measured proper motions for over 1 billion stars, with accuracies sufficient to trace stellar orbits backward through millions of years of galactic evolution. These data sets enable searches for stellar pairs that shared common trajectories in the recent past, potentially identifying systems that have undergone separation within the last few million years. The three-dimensional structure of stellar kinematics reveals complex patterns of motion that reflect the galaxy's gravitational history and the processes that have shaped stellar orbits over cosmic time. Moving groups and stellar streams, elongated structures in velocity space that represent the dispersed remnants of former clusters and associations, provide natural laboratories for studying binary disruption in different galactic environments. Some of these kinematic structures might contain former binary companions that have been separated through cluster dissolution, rather than individual binary evolution. Only took billions of years for galactic tidal forces to gradually stretch and eventually break the gravitational bonds that once connected stellar partners, scattering former companions throughout the galaxy's spiral arms while erasing most traces of their ancient relationships. The process continues throughout the galactic disk as wide binary systems surrender to the cumulative effects of gravitational perturbations, molecular cloud encounters, and stellar interactions that slowly but inexorably separate stars that once shared common origins in the crowded nurseries of stellar formation. The quest to detect hidden stellar companions has driven the development of increasingly sophisticated astronomical techniques that push the boundaries of observational precision and data analysis capabilities. Modern search strategies combine multiple approaches: astrometric monitoring for gravitational wobbles, infrared surveys for thermal emissions, and gravitational microlensing for brief amplification events, creating a comprehensive observational net designed to capture even the most elusive stellar partners. These complementary methods represent astronomy's systematic attempt to explore every possible signature that might reveal the presence of objects too dim, distant, or exotic for conventional detection techniques. Astrometric searches focus on measuring the tiny positional shifts that would result from gravitational perturbations by an orbiting companion. Even a brown dwarf companion with only 1% of the Sun's mass could induce positional wobbles, detectable by space-based instruments if it follows an orbit with periods ranging from decades to centuries. The European Space Agency's Gaia mission represents the current pinnacle of astrometric capability, measuring stellar positions with accuracies approaching 10 microarc seconds, angular scales comparable to watching a coin from the distance of the Moon. The data analysis challenges associated with astrometric companion searches require sophisticated statistical techniques that can distinguish genuine orbital motion from instrumental noise and systematic errors. Stellar parallax measurements, proper motion corrections, and the complex dynamics of solar system motion around the galactic center all contribute systematic signals that must be carefully modeled and removed before weak companion signatures become apparent. The analysis process can take years of careful work to achieve the statistical confidence necessary for companion detection claims. Infrared survey techniques have revolutionized the search for cool stellar companions by systematically mapping thermal emissions from objects throughout the solar neighborhood. The Wide-Field Infrared Survey Explorer WISE surveyed the entire sky at wavelengths between 3 and 22 micrometers, achieving sensitivities capable of detecting objects with surface temperatures as low as room temperature within a few light-years of Earth. Follow-up observations with more sensitive instruments can confirm candidate detections and measure detailed properties such as temperature, mass, and orbital motion. The challenge of distinguishing genuine companions from unrelated background objects requires careful analysis of parallax measurements and proper motions that demonstrate gravitational association. A true stellar companion must share the Sun's motion through space, displaying the same parallax distance and proper motion vector despite being separated by potentially vast angular distances on the sky. This requirement for kinematic consistency provides a powerful filter that eliminates most false positive detections while confirming genuine gravitational relationships. Gravitational microlensing offers a unique detection method that relies on Einstein's general theory of relativity to amplify light from background stars when massive objects pass in front of them. If our solar system harbors a massive companion object, it might occasionally create detectable lensing events as it passes in front of distant stars. The duration and shape of these brightening events encode information about the lensing object's mass and orbital motion, providing independent constraints on companion properties that complement other detection methods. Radial velocity monitoring represents another powerful technique for companion detection that measures the spectroscopic Doppler shifts caused by gravitational reflex motion. High-precision spectrographs can measure stellar velocity changes of a few meters per second, roughly walking speed, over periods of years or decades. A massive companion following an eccentric orbit might produce periodic velocity variations detectable through long-term monitoring programs, though the required observational baseline could span decades for companions at stellar distances. The statistical analysis of stellar wobbles requires careful treatment of noise sources and systematic effects that can mimic or mask genuine companion signals. Stellar magnetic activity, instrumental drifts, and atmospheric variability all contribute noise that must be modeled and removed from the data. Advanced Bayesian analysis techniques allow astronomers to quantify the statistical significance of potential detections while accounting for the complex correlations and uncertainties inherent in astronomical time series data. Space-based infrared telescopes have achieved unprecedented sensitivity for detecting the faint thermal emissions expected from cool brown dwarf companions. The James Webb Space Telescope, with its large collecting area and advanced infrared detectors, can detect objects with temperatures below 100 degrees Celsius at distances of several light-years. Future missions, such as the proposed Wide-Field Infrared Transient Explorer Winter, will extend these capabilities to fainter objects and larger sky areas. The development of adaptive optics systems has enabled ground-based telescopes to achieve diffraction-limited performance that rivals space-based instruments for direct imaging of nearby stellar companions. These systems use deformable mirrors to correct atmospheric turbulence in real time, creating stable images that can reveal faint companions within a few arcseconds of bright primary stars. Chronographic techniques that block starlight from the primary star further enhance the contrast ratios necessary for direct companion detection. Machine learning algorithms have emerged as powerful tools for analyzing the vast data sets produced by modern astronomical surveys. Neural networks and other artificial intelligence techniques can identify subtle patterns in stellar light curves, spectroscopic data, and astrometric measurements that might indicate the presence of hidden companions. These automated analysis methods can process millions of stellar observations to identify the most promising candidates for detailed follow-up studies. The coordination of multiple observational techniques creates synergistic effects that enhance overall detection capabilities beyond what any single method could achieve. Astrometric detections can provide orbital predictions that guide infrared searches for thermal emissions, while radial velocity monitoring can confirm the dynamical nature of candidates identified through other methods. This multi-messenger approach to stellar companion searches maximizes the scientific return from expensive observational campaigns. International collaboration has become essential for companion search programs that require access to telescopes in both hemispheres and coordination of observational resources over extended time periods. Projects such as the Red Dots campaign coordinate observations from multiple ground-based facilities to monitor nearby stars for signs of planetary and stellar companions. These collaborative efforts demonstrate how the global astronomical community can pool resources to tackle challenging observational problems. The false positive rate in companion searches requires careful statistical analysis to distinguish genuine detections from chance alignments and instrumental artifacts. Monte Carlo simulations of the observational process help quantify the probability of spurious detections under different assumptions about noise characteristics and systematic effects. Bayesian model comparison techniques provide rigorous frameworks for evaluating the statistical evidence for companion hypotheses versus null models. Future technological advances promise even more sensitive search capabilities that could finally resolve the question of our Sun's stellar companionship. Extremely large telescopes with collecting areas exceeding 100 square meters will achieve unprecedented sensitivity for direct imaging and spectroscopic analysis of faint companions. Space-based interferometers could measure astrometric signals too small for current instruments, while advanced coronagraphs might enable direct detection of companions with contrast ratios billions of times fainter than their primary stars. The integration of gravitational wave astronomy with traditional electromagnetic observations opens new possibilities for detecting massive companions through their interactions with other objects in the solar system. Future gravitational wave detectors with improved low-frequency sensitivity might detect the orbital decay of close binary systems or the gravitational signatures of three-body interactions involving hidden companions. Only took decades of technological development to create observational capabilities sensitive enough to detect even the most elusive stellar companions. Yet the question of our sun's solitude remains tantalizingly unresolved. Each new generation of instruments and analysis techniques narrows the parameter space where hidden companions could exist, while pushing detection thresholds toward ever more exotic and unlikely scenarios. The search continues with the patient persistence that characterizes astronomy's quest to understand our place in the cosmic hierarchy of gravitational relationships. Throughout the galaxy's spiral arms, binary star systems have given birth to planetary architectures that challenge every assumption about world formation derived from our solitary solar system. These exotic arrangements create gravitational environments where planets follow figure-8 orbits around both stars, experience double sunsets and complex seasonal cycles, or maintain stable orbits despite the chaotic three-body dynamics that govern their motion. The diversity of possible planetary configurations in binary systems suggests that our familiar arrangement of worlds orbiting a single star may represent just one outcome among countless alternatives that stellar companionship makes possible. Circumbinary planets, worlds that orbit both members of a binary star system, trace gravitational paths of stunning complexity as they navigate the ever-changing tidal forces created by two stars in orbital motion. These planets must maintain sufficient distance from the binary pair to avoid destabilizing resonances, typically orbiting at distances several times the stellar separation. The resulting orbital periods often exceed those of any planet in our solar system, creating worlds where years stretch across decades or centuries of terrestrial time, while the binary stars perform their celestial dance in the planetary sky. The discovery of Kepler-16b, the first confirmed circumbinary planet, revolutionized astronomical understanding of planetary formation in binary environments. This Saturn-sized world orbits a pair of stars every 229 days, maintaining a stable orbit despite the complex gravitational field created by its binary hosts. The planet experiences a constantly changing radiation environment as the two stars eclipse each other every 41 days, creating climate variations that have no analogue in single-star planetary systems. Planet formation in binary systems follows different physical processes than those that operated in our solar system, with gravitational perturbations from stellar companions affecting every stage from initial dust aggregation to final orbital configuration. The protoplanetary disks from which planets form can be truncated, warped, or completely disrupted by binary tidal forces, creating gaps and asymmetries that channel planetary formation into preferential locations. These effects can either enhance or inhibit planet formation depending on the specific orbital parameters and mass ratios of the stellar components. The gravitational resonances that stabilize planetary orbits in binary systems create intricate mathematical relationships between orbital periods that maintain long-term stability despite the complex underlying dynamics. Planets in binary systems often occupy resonant chains where orbital periods maintain simple integer ratios, allowing multiple worlds to coexist in gravitational harmony while avoiding destabilizing interactions. These resonant configurations can persist for billions of years, demonstrating nature's ability to find stable solutions even in apparently chaotic gravitational environments. S-type planets, worlds that orbit just one member of a binary star system, experience gravitational perturbations from the distant companion that slowly modify their orbital elements over astronomical timescales. These planets maintain stable orbits around their primary star but experience additional precession, eccentricity variations, and inclination changes that create long-term climate cycles unknown in single-star systems. The timescales for these orbital variations range from thousands to millions of years, potentially driving evolutionary pressures very different from those that shaped life on Earth. The habitable zones around binary stars display temporal and spatial complexity that makes the concept of planetary habitability far more nuanced than simple distance-based calculations suggest. Planets orbiting close binary systems experience radiation from two stars whose combined output varies as the stars move through their orbital cycle, creating habitable zones that expand and contract over timescales ranging from days to years. The definition of habitability must account for these variations and the possibility that life might adapt to cyclical rather than steady environmental conditions. Planetary migration in binary systems follows pathways that can drive worlds into exotic orbital configurations impossible in single-star environments. The combined gravitational influence of two stars creates migration corridors and barriers that channel planetary motion along specific trajectories, sometimes resulting in highly inclined or retrograde orbits where planets circle their stars in directions opposite to stellar rotation. These migration processes can continue over millions of years, gradually reshaping planetary system architecture long after the initial formation phase. The atmospheric dynamics of planets in binary star systems must cope with radiation environments that vary both spatially and temporally as the planets follow their complex orbital paths. Worlds orbiting close binary systems experience double peaks in solar radiation as each star rises and sets, creating atmospheric circulation patterns unlike anything found on Earth. The presence of two stars also affects atmospheric chemistry through enhanced photodissociation rates and complex seasonal cycles that may prevent the development of stable atmospheric compositions. Trojan planets represent an exotic class of worlds that share orbital paths with other planets while maintaining stable gravitational relationships through Lagrange point dynamics. In binary star systems, the increased complexity of gravitational fields creates additional opportunities for Trojan configurations, potentially allowing multiple planets to share similar orbital distances while avoiding direct collisions. These co-orbital arrangements demonstrate the remarkable diversity of stable configurations that emerge from gravitational n-body dynamics. The formation of moon systems around planets in binary environments faces additional challenges from tidal forces and gravitational perturbations that can disrupt the circumplanetary disks necessary for regular satellite formation. The large moons that characterize the giant planets in our solar system might be rare or impossible in close binary systems where stellar tidal forces compete with planetary gravity for control of satellite-forming material. Alternative moon formation mechanisms, such as capture of stray objects, might become more important in binary environments. Asteroid belt analogues in binary systems could display structures and dynamics very different from the relatively simple arrangement found between Mars and Jupiter. The gravitational influence of two stars creates additional resonances and secular perturbations that affect small body populations, potentially creating gaps, asymmetries, and dynamical families unknown in single-star systems. These effects might enhance collision rates and grinding processes that create dust and meteoroid populations with different size distributions and orbital characteristics. The delivery of water and organic compounds to terrestrial planets in binary systems could follow pathways that depend critically on the specific orbital architecture and dynamical evolution of each system. Comet and asteroid populations in binary environments experience gravitational perturbations that might either enhance or reduce impact rates on inner planets compared to single-star systems. The timing and intensity of these bombardment episodes could significantly affect the development of planetary atmospheres and the emergence of conditions suitable for life. Planetary ring systems in binary environments face disruption mechanisms unknown in single-star systems, where the gravitational influence of distant stellar companions can slowly destabilize the orbital dynamics that maintain narrow rings and complex structure. The shepherd moons that create gaps and density waves in planetary rings might be unable to maintain stable orbits in the presence of binary perturbations, leading to ring systems with simpler structure or shorter lifetimes than those observed around the giant planets. The long-term orbital evolution of planetary systems in binary environments includes effects such as Kozai-Lidov oscillations, where the gravitational influence of a distant stellar companion drives periodic exchanges between orbital eccentricity and inclination. These oscillations can occur over timescales of millions of years, potentially driving planets into highly eccentric orbits that create extreme climate variations or even cause planetary ejection from the system entirely. The prospects for life in binary planetary systems depend on complex interactions between stellar radiation, orbital dynamics, and atmospheric evolution that remain poorly understood despite intensive theoretical investigation. The additional complexity of binary environments might actually enhance habitability by creating more diverse evolutionary pressures and environmental niches, or it might prove incompatible with the stable conditions that allowed complex life to emerge on Earth. It only took billions of years of planetary formation to demonstrate that gravitational creativity extends far beyond the simple arrangements found in single-star systems, producing exotic world configurations that challenge theoretical understanding while expanding the possibilities for planetary diversity throughout the galaxy. Whether our solar system's binary absence represents a rare cosmic accident or a necessary condition for life remains one of astrobiology's most intriguing questions. In the deepest reaches of space, where starlight dims to whispers and cosmic time unfolds in billion-year rhythms, our sun continues its solitary journey through the galaxy's spiral arms, carrying its family of worlds through the interstellar dark without stellar companionship. The question of whether this isolation represents cosmic accident or evolutionary necessity settles into the realm of profound mysteries that may never find complete resolution. Perhaps our star's loneliness enabled the delicate orbital mechanics that allowed Earth's temperate climate to persist through geological epochs. Or perhaps we simply exist as statistical outliers in a universe where stellar partnerships represent the norm. The statistical weight of binary star prevalence throughout the galaxy creates a quiet tension between observation and expectation, suggesting that our solar system's architecture may be far more unusual than casual inspection reveals. Computer simulations of stellar formation consistently predict that single stars should represent a small minority of the galactic population. Yet here we orbit a solitary nuclear furnace that shows no obvious signs of ever having possessed a gravitational partner. The contradiction generates ongoing scientific puzzles that motivate increasingly sophisticated searches for hidden companions lurking in the cosmic darkness beyond current detection thresholds. The search for our sun's hypothetical twin has evolved from speculative possibility to systematic investigation, employing the most advanced astronomical techniques to explore ever fainter and more distant objects that might share our star's galactic motion. Each new generation of infrared telescopes, astrometric surveys, and data analysis algorithms narrows the parameter space where stellar companions could exist while pushing detection limits toward increasingly exotic scenarios. The absence of obvious candidates gradually transforms from surprising observation to fundamental constraint on models of solar system formation and evolution. The implications of stellar solitude extend far beyond academic curiosity. touching on fundamental questions about the conditions necessary for life's emergence and the prevalence of habitable worlds throughout the galaxy. If our Sun's isolation proves essential for maintaining Earth's stable climate and the delicate orbital relationships that enabled biological evolution, then the galaxy's preference for binary systems might significantly reduce the number of worlds suitable for complex life. The statistical rarity of single stars could translate directly into the rarity of life-bearing planets, with profound implications for astrobiology and the search for extraterrestrial intelligence. The gravitational dynamics that govern binary star evolution operate on timescales that dwarf human comprehension, creating cosmic narratives where stellar partnerships form, evolve, and dissolve over periods measured in billions of years. The galaxy serves as an enormous laboratory for gravitational experiments that test the stability of stellar relationships against the cumulative effects of molecular cloud encounters, tidal forces, and three-body interactions that gradually reshape the orbital architecture of stellar systems. Our Sun may represent either a system that never formed binary partnerships, or one that lost its companion through processes too gradual to preserve observable traces. The ongoing search for solar siblings, stars born from the same molecular cloud that gave birth to our Sun, continues to reveal the complex processes that disperse stellar families throughout the galaxy's disk. Chemical tagging and kinematic analysis provide increasingly powerful tools for identifying genuine stellar relatives among the vast population of field stars, though definitive confirmation requires combining multiple lines of evidence that challenge current observational capabilities. The discovery of even one confirmed solar sibling would provide crucial insights into our star's formation environment and the processes that determined its current isolation. The diversity of planetary architectures in known binary systems demonstrates the remarkable gravitational creativity that stellar companionship enables, producing world configurations that have no analogues in our familiar solar system. Circumbinary planets, Trojan worlds, and complex resonant chains reveal the exotic possibilities that emerge when planetary formation proceeds under the influence of multiple stellar masses. These alternative arrangements challenge theoretical understanding while expanding the parameter space of potentially habitable environments, suggesting that life might find ways to flourish in gravitational conditions far removed from Earth's stable orbital relationships. The technological evolution of companion detection methods continues to push toward ever greater sensitivity and precision, driven by the fundamental question of whether our solar system harbors objects too dim or distant for current instruments to reveal. Future space-based interferometers, extremely large ground-based telescopes, and advanced data analysis techniques promise to explore previously inaccessible regions of parameter space where brown dwarf companions or distant planetary objects might lurk undetected. The negative results from each new survey provide increasingly stringent constraints, while the possibility of discovery maintains scientific motivation for continued searching. The philosophical implications of cosmic solitude resonate through multiple scales of astronomical investigation. From the intimate gravitational relationships within our solar system to the broader patterns of stellar formation and galactic evolution that shape the universe's structure, our Sun's apparent isolation might reflect fundamental physical processes that govern star formation, or it might represent a chance outcome in the complex gravitational lottery that determines stellar multiplicity. The question touches on deep issues about the role of contingency versus necessity in cosmic evolution and the uniqueness of the conditions that enabled our existence. The gravitational archaeology that seeks to reconstruct our solar system's hidden history continues to evolve as astronomers develop increasingly sophisticated methods for reading the subtle signatures preserved in planetary orbits, asteroid populations, and comet reservoirs. The cone arrangement of worlds around our Sun carries encoded information about the gravitational environment that existed during planetary formation, though deciphering these clues requires careful modelling of 4.5 billion years of orbital evolution. Each new theoretical insight and observational constraint adds pieces to the puzzle of our solar system's formation and early evolution. The cosmic perspective that emerges from contemplating our Sun's journey through space reveals the profound interconnectedness of astronomical phenomena across vast ranges of scale and time. Our star's motion through the galaxy carries it through regions of varying stellar density, molecular cloud encounters, and gravitational perturbations that could have influenced the evolution of life on Earth through mechanisms both subtle and dramatic. The absence of obvious stellar companions may represent one of many factors that created the stable, astronomical environment necessary for biological complexity to emerge and persist. The mathematical beauty of gravitational dynamics creates elegant solutions to the three-body problem in systems where stellar companions maintain specific orbital relationships, demonstrating that even chaotic-appearing gravitational interactions can produce stable, long-lived configurations. The study of binary star systems reveals the remarkable diversity of stable solutions that emerge from relatively simple physical laws, suggesting that our solar system's architecture represents just one possibility among countless alternatives that different initial conditions might have produced. The observational challenges associated with detecting the most elusive stellar companions continue to drive technological innovation in astronomical instrumentation and data analysis techniques. The quest for our Sun's hypothetical twin pushes the boundaries of what current technology can achieve, while motivating the development of future observational capabilities that will extend the search to even fainter and more distant objects. Each advance in sensitivity opens new windows for discovery, while revealing the remarkable emptiness of the space immediately surrounding our solar system. The temporal scales involved in stellar evolution and galactic dynamics create a cosmic context where our current observations represent mere snapshots of processes that unfold over billions of years. Our Sun's present isolation might reflect a temporary configuration in a longer gravitational narrative that includes periods of stellar companionship, separated by epochs of solitary travel through the interstellar medium. The galaxy operates as a vast recycling system where stellar partnerships form and dissolve according to gravitational processes that operate with geological patience. The statistical mechanics of stellar formation in molecular clouds continue to provide theoretical frameworks for understanding the multiplicity distribution observed among field stars throughout the galaxy. Computer simulations of turbulent fragmentation and gravitational collapse suggest that the initial conditions during star formation largely determine whether stellar systems emerge as singles, binaries, or higher-order multiples. Our Sun's solitude might reflect specific properties of the molecular cloud environment where it formed rather than subsequent evolutionary processes that removed hypothetical companions. The energy scales involved in stellar formation and early evolution create conditions where relatively small changes in initial parameters can lead to dramatically different outcomes in terms of stellar multiplicity and planetary system architecture. The chaotic nature of gravitational interactions during cluster dispersal means that slight variations in stellar positions or velocities can determine whether binary systems survive or dissolve as young stellar associations gradually spread throughout the galactic disk. The silence of deep space surrounds our solar system with a quietude that has persisted for billions of years, broken only by the occasional passage of interstellar objects that carry news from distant stellar systems. The absence of nearby stellar companions creates a gravitational environment of remarkable stability, where planetary orbits maintain their characteristics over geological timescales, enabling the gradual processes that transformed a young Earth into a world capable of supporting complex life. Only took 4.5 billion years for our Sun to establish its current status as a gravitational singleton. Whether through formative processes that never produce stellar companions, or through evolutionary mechanisms that gradually separated our star from hypothetical partners, the cosmic loneliness that characterizes our solar system may represent either a rare accident of stellar formation or a necessary condition for the emergence of stable, temperate worlds where life can flourish across cosmic time. The search for our Sun's companion fades into the realm of cosmic meditation, where questions dissolve into the deeper rhythms of galactic time and stellar motion. In the vast darkness between stars, our solitary Sun continues its ancient journey around the galaxy's center, carrying its family of worlds through regions of space that will not repeat their current configuration for hundreds of millions of years. The absence of stellar companionship creates a gravitational silence that has persisted since the solar system's youth, enabling the delicate orbital relationships that maintain Earth's temperate climate and the stable conditions necessary for life's long evolution. Perhaps in some parallel universe, our Sun burns as part of a binary system, its hypothetical companion creating complex tidal forces that prevent stable planetary orbits or drive worlds into eccentric paths unsuitable for biological evolution. Perhaps in that alternative cosmos, no blue planet maintains liquid oceans for billions of years, no continents drift slowly across a world's surface, no complex chemistry emerges from the interplay of stellar radiation and planetary geology. The cosmic dice that determined our solar system's architecture may have rolled precisely the combination necessary for consciousness to emerge and contemplate its own origins. The billion-year rhythms of galactic evolution continue their ancient dance while our Sun drifts between the spiral arms, neither seeking nor avoiding stellar encounters that might reshape the outer boundaries of its gravitational domain. The Oort Cloud maintains its spherical watch at the edge of solar influence, occasionally releasing icy messengers that carry tales of the deep freeze to the inner worlds where seasons change and life adapts to the subtle brightening of an aging star. In this cosmic solitude, the profound silence of space becomes a meditation on time itself, where human concerns fade into the larger patterns of stellar birth and death that shape the galaxy's ongoing evolution. Our Sun's journey through space represents just one chapter in a vast library of stellar stories, most of which involve the gravitational partnerships and binary dances that characterize the galaxy's preferred social arrangements. Whether our solar system's isolation enabled or hindered the emergence of life remains one of the universe's unsolved mysteries, a question that may find answers only when we discover other worlds orbiting other solitary stars in the cosmic dark. The search for our Sun's twin dissolves into the patient rhythms of astronomical time, where instruments gradually achieve greater sensitivity, while the cosmos maintains its secrets with the same gravitational patience that governs stellar formation and galactic evolution. In the end, perhaps the question matters less than the searching itself. The human impulse to understand our place in the vast hierarchy of cosmic relationships that connects our small world to the largest structures of space and time. Sleep settles over this cosmic meditation like interstellar dust, accumulating in the quiet regions between stars, where even the faintest radiation pressure cannot disturb the ancient silence that has persisted since the galaxy's youth.